He went on to earn his Doctorate of Science in Electrical Engineering with a specialization in computer science from the Massachusetts Institute of Technology. Professor Bagchi has held prestigious positions at institutions such as Yale University, IIT Kharagpur, and IIM Calcutta. He has served 2 terms as member of the Board of Governors at IIM Calcutta from 1990 to 91 and again from 1997 to 1999. In July 2007, he joined the Indian Institute of Science Education and Research, Calcutta, where he held the position of Professor and Chairman, Department of Mathematical Sciences. In July 2010, after retiring from IISER, he joined us at Heritage Institute of Technology as a professor of computer science and engineering. In March 2015, he became an emeritus professor. So he has served as visiting professor at the following US universities: Computer Science Department, University of Illinois at Urbana-Champaign, School of Management, New Jersey Institute of Technology, and School of Management at University of Texas at Dallas. His academic research contributions span areas including internet auctions, representation and verification of workflows, software reliability, heuristic optimization, internet-based applications, search methods in artificial intelligence, resource-constrained project scheduling, job scheduling and sequencing, and rectangular stock cutting. Additionally, Professor Bagchi has served as a mentor to numerous doctoral students in these areas. He is listed in the marquees who's who in the world. His wide-ranging expertise makes him a perfect fit for today's session, and we are privileged to have him here with us. Please join me in welcoming Professor Amitabh Bagchi to introduce Professor Bhashar Bhattacharya, who will connect with us online. So please.
Thank you, Aritra. Very happy to be present at this conference. Let me introduce Professor Ashok Bhattacharya. I don't know him personally. I only know his father. But Ashok was a student at the Indian Statistical Institute, and I think he did his BTech and MTech from there, so he's a statistician. And later on, he studied at, I think it is Stanford, no? He studied there, and the work is mainly statistical. He is currently a faculty member at the very well-known management school at Wharton. Okay, so the title of his talk is Competitive Facility Location. Okay, and Discrete Voronoi Games. Okay, so let us hear him. It will be online. The presentation will be online. Thank you.
Thank you. Am I audible? Should I start?
Bhashata, you may start.
Okay, thank you. Thank you, Professor Bagchi, for the kind introduction, and thank you for the organizers for inviting me to give this talk. I first want to begin by apologizing for not being there in person. I was supposed to be there, but I had to come back to the US earlier than I had anticipated to do some official paperwork. So apologies for that. So this is a sort of a survey talk on some problems about competitive facility location and discrete Voronoi games that we have been thinking on and off for the last several years. Let me sort of begin with giving a roadmap of the talk and also a personal anecdote. So I started thinking about these facility location and geometric optimization problems when I was doing my undergraduate, my BStat work at ISI Calcutta almost 20 years ago now. And although I did keep on thinking about these problems a little bit after I left ISI, my PhD work and subsequent work was in probability and statistics. So I kind of moved away from this a little bit. And then when I started my job here at the University of Pennsylvania around 8 years ago, a few months after that, I got an email, a cold email out of nowhere from a colleague of mine who I didn't know at that time from the epidemiology department. So his name is Ricardo Castillo-Nera, and I'll talk about him later. And so he reached out to me and he asked, so they were working on designing some vaccination campaigns for rabies in Peru in South America. And they wanted some help with geometric optimization algorithms and some statistical modeling. And they saw that I had some work on that before, so they reached out. So that's how I kind of got back to thinking about these problems that I thought about when I was an undergraduate student. And it was through working through with Ricardo's group that we ended up realizing that the new theoretical problems that emerged by discussing the project with them. So I started off in theory. By some lucky coincidence, I got involved in some applications. And it is through these applications that led to new theoretical problems. So this is why I said in the title, from theory to practice and back. And that is sort of the broad roadmap that I'm going to follow in this talk as well. So I'm going to start by sort of some theory and background of the fundamentals of some facility location problems. We'll discuss, followed by that, we'll discuss some of our results on competitive facility location and Voronoi games. And in the end, I will talk about the rabies project and discuss how these ideas were relevant there and how that itself led to new problems. So throughout this talk, you will notice that there will be many questions. I will mention lots of open problems and lots of questions. There will be more questions than answers, really. So some of the most interesting thing in this area, we don't really know what to do. So there's lots to do here and lots to think about. Okay, so let me start from the basics and discuss some background and history about facility location problems. So one of the most classical and well-known problems in facility location is the one median problem, which is also called the Fermat-Weber problem. So you have a set of users P1 to Pn, and these are users on the plane. Think of the plane throughout the talk, but it can be done on RD. So we have some points on the plane, and these are my users, and I want to find a facility, a new point Q, such that the users don't have to travel too much to get to the facility. You don't want them to go a long distance. So a natural way to sort of optimize the placement of this facility Q is to minimize the sum of the distances from the users to the facility. So the one median problem, or the Fermat-Weber problem, is to find a point Q which minimizes the sum of distances, the sum of Euclidean distances from the points Pi to the point Q. So when d is equal to 1, when you are doing this in one dimension, and when the points are on a line, well, it's a very basic exercise in statistics to realize that the minimization problem is attained at the median of these points. So if you have a bunch of points on the line, you want to minimize the sum of the absolute differences. What you get is the median. So in dimension 1, the solution of this problem is the median. Now, this problem in dimension 2 was first proposed by Fermat for 3 points. So Fermat asked, if there are 3 points ABC in the plane, what's the point Q such that the sum from Q to ABC is minimized? So we'll come back to Fermat's problem and the solution in a moment. But this problem later on was appeared in work of Alfred Weber in the context of facility location. That's the setup I just mentioned. So we have the name, the Fermat-Weber problem. Now, in the statistical context, this problem was studied by Halden, by JBS Halden, and he used this as a notion of a multivariate median. So because in dimension 1, this problem gives the median, defining median in dimensions more than 1 is a delicate matter because there is no natural notion of ranking. And Halden used the solution of this optimization problem as a natural notion of median. So for dimensions greater than or equal to 2, the one median problem, the optimum solution Q star of this problem, is often called the geometric median. So as I mentioned, this problem has a long history and it goes back to Fermat. And Fermat asked this problem for 3 points. If you have 3 points in the plane, he asked to find a point Q such that the sum of Q to the 3 points A, B, and C is minimized. So a few years after Fermat proposed this problem, Torricelli found a solution. And the solution is quite interesting. It's not one of the standard points you get in classical Euclidean geometry. So the solution of the point, which minimizes the sum of distances, is the point which subtends angle 120 from each of the sides. So it's that point here, such that the angle from all the sides to this point is 120. So that point is called the Fermat-Torricelli point. Okay? Now, this solution is only a valid solution if all the angles of the triangle itself is less than 120, right? Because if one of the angles is bigger than 120, this point will be outside the triangle. So there's no reason to put this point outside the triangle. So Torricelli didn't really realize that, and he solved this problem implicitly under the assumption that all the angles are less than 120. Now, what happens if one of the angles is bigger than 120? So in this case, if you think about it, a natural guess for the Fermat point would be this vertex which is obtuse. The angle where it is greater than 120, that vertex itself is a guess for the solution. And that is indeed the solution, but the proof of that, correct proof of that was missing from the literature for many, many years. So in this case, the solution, the optimum solution coincides with the obtuse vertex. This was kind of folklore, but this wasn't really done formally for many years. It was missing in Torricelli's argument. It was noticed later in the famous book by Courant and Robbins that this case is missing. There were some incorrect proofs given over the years. And finally, in 1997, which is much more recent, Karup and Vatja gave a solution which said that the optimum solution is that obtuse vertex. Okay? Now, there are a few other cases where the solution of the Fermat-Torricelli point is well known. So instead of 3 points, now suppose I have 4 points. So in this case also, you can describe the Fermat-Torricelli point explicitly. So if the 4 points lie in a convex position, in a convex quadrilateral, then the Fermat-Torricelli point is the intersection of the diagonals. And I think this can be shown by some triangle inequality kind of argument, but okay, it's the intersection point of the diagonal. Again, this is classically known from the 1700s. The case that was missing is when the points are not in convex position. So the left figure here shows the Fermat point here, which is the intersection of the diagonals. But in the right side, I have a situation where the 4 points are not in convex position. So when the 4 points are not in convex position, the Fermat-Torricelli point is the non-convex vertex, this point right here. But this was again missing from the literature for a long time, and Frank plus Tria only relatively recently showed that the non-convex vertex is the solution of the Fermat-Torricelli point if the 4 points are in not convex position. So for 3 points and for 4 points, the Fermat-Torricelli point can be easily described. Now, in general, there are no closed form solutions of the Fermat-Torricelli point, and not even in dimension 2. In fact, there is a very interesting result of Bajaj, which says that even if you have 5 points in 2 dimensions, then it is impossible to construct the Fermat-Torricelli point using a ruler and a compass. So with 5 points in 2 dimensions, I cannot construct it with a ruler and a compass. So explicit geometric location of this point is hard, in fact, impossible in certain geometric sense. And so in general, these problems are solved using iterative algorithms. And one of the most well-known ones is Weisfeld's algorithm from 1937, which is a very simple algorithm which gives you a way to solve this problem. Weisfeld's algorithm doesn't always converge, but it's still a useful algorithm which is, practically very relevant. And over the years, there has been a long line of work in trying to develop efficient approximation algorithms for these problems. So you want to find a point which comes, whose cost comes 1 plus epsilon close to the true cost in time, which is polynomial in the number of points. And so there is many, many results on that. And one of the sharpest known results is a paper by Cohen et al., which gives a almost linear time algorithm for a 1 plus epsilon approximation for the Fermat-Weber point. Okay. So that's the Fermat-Weber point. That's the one median problem. There is another problem which goes hand in parallel to this, which is the one center problem, where instead of minimizing the sum of distances, your goal is to minimize the maximum distance. So you have a set of users P1 to Pn, and you want to find a point Q such that the maximum distance from P1 to Q is minimized. This is also a natural objective. You want to minimize the maximum that someone has to walk, and that is known as the one center problem. So the one center problem, if you think about it, the center, the solution Q star, where the solution is attained, if you draw a circle with center at Q and radius the optimum distance, this will enclose all the points, and this will be the center of the minimum enclosing circle, the circle of smallest radius that encloses all the points. And if you know what it means, the minimum enclosing circle will always lie on what is called the farthest point Voronoi diagram of this set of points. It's not super relevant here, but there is a nice geometric characterization of where this point is supposed to lie. And there is famous paper of Megiddo from 1983, which gives a linear time algorithm for solving this problem. So these are 2 classic variants of facility location problem, the one median and the one center. Now, both of these problems involve placing a single facility given a set of users, but they naturally extend to placing more than one facility. So they naturally extend to the k-median or the k-center problem. So what is the k-median problem? I have, again, a set of users P1 to Pn, and I want to place k facilities, not one, but k of them in a certain way. How so? Well, I look for every user to the closest facility, and I look at the distance of Pi to the closest point in Q. Call that dPi of Q. The k-median problem is to minimize the sum of distances from every user to its closest facility. And the k-center problem is to minimize the maximum distance of every user to its closest facility. It's the exact same problem as before, but for every user, you are measuring the distance to its closest facility. So if you do the sum, you get the k-median. If you do the maximum, you get the k-center problem. So both these problems are, widely studied. There is massive literature on both of them. They are hard problems if k is part of the input. If k is part of the input of your problem, they are both hard. And there is a long line of work to study exact algorithms, approximation algorithms for these problems. Now, the efficient algorithms that people do are sophisticated, delicate methods. But if you want to actually implement some of these, it's quite difficult. So in practice, certain heuristic algorithms are used. So there are local search algorithms, greedy swap algorithms, which are done. And you run these and you get a solution. So this is how these things are done. And I'll come back to these problems later on in the talk when I mention the applications. So broadly speaking, these are 2 classes of problems that people look at in facility location. The goal here is to place a bunch of facilities given a set of users, and you optimize a certain criteria. Sum of the distances is one criteria. Maximizing the minimum distance, Minimizing the maximum distance is another criteria. So let me now introduce the competitive versions of these problems. So in a competitive facility location problem, you have two types of players, two types of facilities who belong to different companies. And their goal is to compete with each other. So company one has some facilities and company two has some facilities. They are serving the same set of users. And the idea is that each company wants to place their facilities in a way so that it can maximize its own gains, maximize the number of users they possibly serve. So that's the competitive version of these problems. Many versions of such problems can be devised. Let me start with a very basic one, a very natural one. So this is the maximum coverage problem. So suppose I am given n users in the plane and m facilities. So they are given to you. Some users are there and some facilities are already there. Throughout this talk, I'm going to assume that every user will go to its nearest facility. So whoever is near to me, I will go to that. What is the goal of the maximum coverage problem? Well, now, suppose a competing company comes in and wants to place a new facility F star, such that the new facility serves the maximum number of users. So F star comes from a competing company, and the goal of F star is to place the point so that it gets its own gain is maximized. So find a location of a new facility F star, which serves the maximum number of users. So in other words, I want to find an F star which is closest in distance to the maximum number of users in U. So here is a setup. I have 5 users, which are marked here in red. And I have 2 existing facilities, F1 and F2. I want to place a new facility F star, which serves the maximum number of users. How do I do that? Okay. So here is how it's done. So it's quite simple, and it takes a moment's thought, but it's quite simple. So for each user, you look at the distance of that user to its nearest facility. So call that distance Ri. So Ri is the distance of Ui to its nearest facility. And draw a circle whose center is Ui and whose radius is Ri. So for each user, each red point, find its closest blue point and draw a circle with the center at the red point and the radius from the blue to the red point. Each of these circles will contain no other blue points inside because it chose the closest blue point. So I will have n circles for each of these users. Consider the arrangement of these n circles, C1 to Cn. Where do I place the optimal facility F star? If a facility is inside a circle, that means it is closer to the existing facility. So what I have to do is I have to place F star at the point where the maximum number of circles overlap, right? So look at this gray area here where 3 circles overlap. That is a region of maximum depth in this arrangement of n circles. So the new facility should be placed at any cell where the maximum number of circles overlap. So that's a classic computational geometry problem. If you do a line sweep, this can be done in n squared log n time. You can be a bit more clever, do some divide and conquer, and get rid of that log n, and do this in n squared time. So which means the maximum coverage problem, the solution of this new point, can be found in n squared time. In fact, it can be shown that this problem is 3-sum hard, which means it is as hard as finding out whether the sum of 3 numbers is 0. So it's n squared is essentially tight. I mean, okay, up to whatever, it's 3-sum hard. Yeah. So this is a tight result. Now, this is true when there are more than 2 existing facilities. If there is a single existing facility and you want to place one more, so M is the number of existing facilities, remember. M is the number of existing facilities. So we have 2 here. But if you have a single existing facility and you want to place one more, then this problem is much simpler and essentially like a sweep, essentially like a rotation sweep. And this can be done in n log n time. It's much faster. So I'll come back to this m equal to 1 case later because it will be relevant. But this is how you solve a prototypical simple competitive facility location problem where you have to place a new point such that it serves the maximum number of users. Okay? Okay, so this problem of placing a single point such that the maximum number of users served is such that the number of users served is maximized can be easily extended to placing not just one, but k points. Just like one median to one k median, like one center to k center, we have the k max coverage problem. So given a set of users and a set of existing facilities, what you do is you want to place k new facilities. So a new company comes in and says, I'm not going to place one, but I'm going to place k facilities. And my goal is to ensure that the number of users served by these facilities in total is maximized. So the union of the number of users served by these facilities is maximized. So just to introduce a little bit of notation to write this out formally. So for every new facility F, script U of F union F star is the number of users, is the set of users which are closer to F than to the other facilities. F script F is the existing facility, F star is the one you put down. And you want to minimize this union. You want to minimize the union of the number of users served by these new facilities, right? So that's the K-Max-Cov problem. So a very simple example will tell you that to solve the K-Max-Cov, it might not be a good idea to place one of the facilities at the maximum depth. Remember, to solve the Max-Cov problem, I have here like 5 users and I have like 5 users and 5 existing facilities. And to solve the Max-Cov problem, I would have to put the new user, one of them, at this gray cell where the depth is maximized. But that is not the correct thing to do if you want to place 2. If you want to place 2, it is good to sacrifice a little bit from each of them so that the union is maximized. So the optimum solution in this case is to place F and F star, these square blue squares somewhere here and here, whose union essentially covers all the facilities. So the optimum positions may not be in the cell of maximum depth, and you have to search over possibilities to solve this problem. So how do you solve this problem? So again, restrict ourselves to the case of the 2 Max-Cov because it's easier to explain. So I want to place 2 new facilities whose union serves the maximum number of points. So as before, I draw my circles. So for each user, I denote by Ri the distance to the closest facility, and Ci be the circle, each centered at the users, passing through the closest facility. And I have these n circles, C1 to Cn. I just showed you these circles, right? These circles right here. Okay, so for the 2 Max-Cov problem, I have to place 2 facilities F and F prime in such a way that the number of users served by F union the number of users served by F prime is maximized. How do I do that? Okay, so suppose a new facility F is the first facility is placed in some cell. Let's go back to this picture. So let's say the first facility is placed here. Then what is the optimum choice of the second facility? Well, what we have to do is that this facility already serves these users. It's done. So I will remove the circles containing F and then find the cell of maximum depth in the remaining arrangement. So you have your first point, it serves some users, remove the circles that point contains and find the point of maximum depth in the remaining arrangement. So that's an algorithm. So you suppose the point F is made up of k circles, lies in a cell which is made up of k circles. Remove those k circles and find the cell of maximum depth. Place F star there. So if you search over all cells and do this, in a brute force manner, this gives you a naive n to the 4 algorithm, which is like trivial, but this is what it gives you. But of course, you don't need that much time because if you have a good data structure which can delete and insert circles efficiently, then you can save a lot of time. And so using what is called a segment tree data structure, which allows you to include and delete circles in an efficient manner, you can improve the running time to n cubed log n. And in general, you can show that the K-Max-Curve problem can be solved using, a very similar idea in time, which is n to the 2k minus 1 log n, and space, which is n squared log n. So this problem is in the Euclidean distance. Throughout the talk, I'm basically focusing on the Euclidean distance, where distance is measured from each user to the closest facility in the Euclidean distance. But you can ask the same questions in other distances, in L1 distance, in L infinity distance. So there, instead of circles, you deal with squares, and you can get similar types of results there. So that those are possible. But several questions remain. The dependence on K that we get in this algorithm, I think, is far from best possible. I think there is a lot of scope to improve that. How do you improve the dependence on K here? I don't know. It's something to think about. If K is part of the input, these problems are likely to be NP-hard, like all the K-median, K-center problems. But again, I think that hasn't been proved. And again, if it is hard, then you think of approximation algorithms and how they are done. All of that, largely remains unexplored. Okay, so that's the K-Max-Curve problem. That is an example of a competitive facility location problem. Let me sort of discuss that this is a problem where the demand set, the user set, was discrete. There is a parallel line of work where you look at the Max-Curve problem for continuous demands. So when the demand set is continuous, it means that you have a square or a convex region, and you are placing some facilities there, and your payoff is measured in terms of the area of the Voronoi cells that you serve. So formally, if you are given a set of M facilities in a bounded convex region, I want to find a new point F star such that the area of the region served by F star, the Voronoi cell of F star, the area of the Voronoi cell of F star is maximized, right? So again, a classical problem. So Dene et al., almost 20 years ago, proved some nice properties of this area function. So they essentially showed if the points in F are in convex position, then the area function of F star, this new point, essentially has a unique local maximum if you don't allow the Voronoi neighbors to change. So kind of like a locally convex function in some ways. Later, Cheong et al. Give a very nice linear time algorithm that locates this new point F star up to an epsilon approximation. So it finds a new point whose area is at most 1 minus epsilon times the best possible area in nearly linear time. Is there a question? Okay, thank you. So the paper, which does this, has a very interesting name, and so I put it there. So it's called On Finding a Guard That Sees Most and a Shop That Sells Most. So it addresses two problems, an art gallery type problem and this facility location problem, and it came up with this very catchy name. Okay, so that's Max-Curve problems, problems where you want to place a single point to maximize the payoff, the number or the area of the Voronoi cell of that point. Let me now talk about the game theoretic versions of this problem. So a Voronoi game is a competitive facility location where there are two players who play the game sequentially, and each of them has the ultimate goal to maximize their own payoffs. So here is the abstract formulation of a Voronoi game. You have a bunch of users in some playing area A. The playing area usually will be a line segment or some rectangle. And we have two players, P1 and P2. Player 1 will first place a facility. Player 2 will then place another facility. And this will go on for R rounds. They will play the game for R rounds. And the goal is of each of the players is to maximize the number of users it serves. So maximize their own payoff. The payoff is the number of users that a particular player serves, after the end of the game. And the player which has the larger payoff will win the game, of course. So this is referred to as the R-round Voronoi game, and we will consider many versions of this in the next few slides. So this has a long history as always, and it goes back to works of Hotelling and Stackelberg in the economics literature first, and then more recently in computational geometry. So let me start with the very basic case when the playing area is a line segment. So you have users on a line segment, and I play this game for R round. How do you do it? What are my optimal strategies? So let's start with a very simple case where I'm playing the game on the line for one round. I have my users E1 up to UN on the line, and I will play the game for one round, which means player 1 will place a point F1, followed by player 2, which will place a point S1. Right. So what is the optimal placement of player 2? So player 2 will make the move after player 1 has made the move, right? So suppose you have your users on the line, these black points are your users, and player 1 has placed at the blue point somewhere. What does player 2 do? This is on the line, this is very easy. So player 2 will look on which side of F1 there are more points and place their facility right next to F1 on that side. So place S1 immediately to the next of F1 on the side that has more users. So the optimal strategy of the second player is trivial. What is the optimal strategy of the first player? The first player will have to make sure that his own payoff isn't sacrificed too much at the end of the game. Now notice if the first player places here, his eventual payoff becomes 3. But the first player could have done better if he placed here, because then his payoff would have been 4. He would have got one side. So to ensure that they protect themselves from the best possible strategy of the second player, the first player has to ensure that the number of users on both sides are balanced, are equal. So the optimal strategy of P1 is at the median. You place it at the median, which ensures that I at least get half. If I don't place at the median, the second player will steal more than half from me, right? So here, this is what F1 does. So one thing to note in this argument is that in wherever F1 places their facility, whether or not F1 is playing optimally or not, wherever the placement of F1 is, if S1, which is the second player, can always at least get half fraction of the users. So P2 can always get half fraction of the users irrespective of the placement of the first player. So in other words, what this means is the second player can always tie the game. The second player will never lose. The second player will always tie. And this is something that we'll come back to again. This is an important point that we'll discuss again. But this is a very simple case where you're playing only one round on the line. What if I play 2 rounds? So already for 2 rounds, you will see that things become more interesting. So I have my users on the line, and I want to play the game for 2 rounds. So F1 will go, P1 will place F1, P2 will place S1, then P1 will place F2, and then P2 will place S2. That's how it goes. So in this case, the optimal strategy is much more complicated. It involves many cases. But we can still ask about worst case payoffs. So for instance, for the second player, we denote by eta 2 of U the maximum payoff P2 can attain against any strategy of P1. Whatever be the strategy of P1, this is the minimum that the second player can get. This is what we call eta 2. And eta 1 is similarly defined. And if I look at the worst possible value of eta 2 of U over the placement of the users, I get eta 2. So eta 2 is the worst possible value of the maximum payoff. So if I lower bound eta 2, that means that P2 will at least get these many users irrespective of the choice of U. So how does eta 1 and eta 2 behave? That's a natural question. So a trivial argument shows that eta 1 is always greater than n over 3. The first player can always get at least n over 3 users. Whatever be the strategy of the second player, whatever be the arrangement of the users, 1/3 of the users I can always get, the first player. And this is a trivial strategy. The strategy doesn't look at the strategy of the second player. All it does is it places F1 such that there are n/3 points to the left of it, and it places F2 such that there are n/3 points between F1 and F2. So it splits the line into 3 parts such that the number of users in each part is approximately n/3. Now, when the second player will play, because the second player places 2 facilities, one of these intervals has to be empty. And that entire interval will then be served by the first player, which gives you the bound of n/3. Now, that is a trivial bound. Now, you wonder if this can be improved. Now, of course, given certain users' placement, this can be improved. But in the worst case, remember, I'm taking a minimum of all users, so it's a worst case. In the worst case, there is an arrangement of users for which this bound is surprisingly tight. There is a set of n users you can place on the line, such that for this set of n users, the first player, no matter how clever he is, cannot get more than n/3. So there exists a strategy which the first player will get n/3 for a certain set of users. And here the placement essentially is to place the points on a geometric series, and that kind of messes things up. So in summary, what it means is that if you divide eta1 over n, the limit is essentially 1/3. I mean, one is floor of n/3, one is ceiling of n/3, so all really the same. So eta1 over n in the limit is 1/3. But what about eta2? What about the second player? What is the minimum that the second player can guarantee? Is there a bound on that? So let's try to understand and see that. So to understand the strategy of the second player, we have to first note that the first player has made his move. So F1 is already placed. So let's say F1 is placed at a point here, such that there are k points to the left of it and n minus k points to the right of it, and k is less than n/2. Now in round 1, the second player will make the following move. The second player will place the point S1 such that there are n/2 users between F1 and S1. So it will go on the right n/2. That's the move of the second player in round 1. Okay? Now let's go to round 2. Round 2 is a bit more complicated. It depends on what the first player did in round 2. So there are 3 cases. The first player can place in this interval, or this interval, or that interval. If the first player places in this interval, the leftmost interval here, what does the second player do? Well, the second player can just place right next to F1. And then this entire interval is the second player's. So it gets n minus k, which is at least n/2. If the first player places in the middle interval, what does the second player do? Well, the second player will place to the left of F1. And then the second player will get this k and this n/2 minus k, which adds up to n/2. And there's a third case which remains, which what if the second player places on the right interval here? And then again, the first player places in the right interval here. The second player will place right next to F1 in the middle interval and get all of the middle interval, which is n/2. So what does this show us? It tells us that in the 2-round game, whatever be the arrangement of the users, the second player can always get n/2 ceiling. Okay. So in other words, the second player can always tie the game, even if it is played for 2 rounds. We saw that trivially the second player can tie the game if it's played for 1 round, but it can also tie the game if it's played for 2 rounds, which is interesting, right? The first player can be very far from winning the game if you have a weird set of users, but the second player will never lose, can always tie the game. So this is 2 rounds. What about general R rounds? So in general, if you play the game for R rounds, by doing the same argument of placing, things at equal intervals, you can show that eta1, the first player's worst case payoff, is 1 over R plus 1 in the limit. Like you place R points so that each of the intervals contain n over R points, And this gives you a payoff limit of 1 over r plus 1. The argument extends exactly. But what about eta 2? Eta 2 is much more delicate. Here, we have a bound which is far from half. It says for the r round game, when r is greater than 3, eta 2 over n is greater than something, this constant. And this constant is of the order 1 over square root of r. So it can always get a constant fraction of the users. It can always get a constant fraction of the users. And the constant fraction is n over square root of r approximately. So approximately n over square root of r it can get, where r is greater than the number of rounds. Now, is this bound tight? We don't think so. So it turns out that we tried to do analysis for r equal to 3, and we did a lot of cases, but we didn't end up fixing all of that because there was a lot of cases. But there is a conjecture is that for any r rounds, this lower bound is actually a half, which means that whatever be the number of rounds that the game is played, the second player will always tie the game. As I mentioned, this is true for r equal to 1, and this is true for r equal to 2. We conjecture this is true for all r. Now, irrespective of whether or not this is true in general, improving this bound right here, this 1 over square root of r bound right here, is an important problem. And this is like a puzzle, and if you have some time, you can think about it. This is like one of my most favorite problems. I think, there is a possibility that this conjecture, if this conjecture is true, why this is interesting, because it says that whatever be the arrangement of the users, however crazy the user arrangement is, the second player will never lose if you play the game r rounds. So that would be interesting. Anyway, so that's the r round game when you play it on the line. So already you see, we understand it pretty well, maybe for r equal to 1 and 2. For general r, it's quite delicate. What about the game in 2 dimensions, which is a more natural problem? You have points, users in the 2-dimensional plane, and I want to play the game there. So again, let's start with the case where I play the game for only 1 round, a single round. So I have my points u1 up to un now on the plane, not on the line. And I play the game for 1 round. So f1 will place a point, p1 will place a point f1, p2 will place a point s1. So given a placement of f1, how do you place the second, how does the second player move? Well, that's pretty easy. I have my users here, and let's say f1 is placed here. So what I want to do is I want to find a line through f1 which has the least number of points on one side. Because if I then place my s1, which is my second player, close to this point on the other side, the perpendicular between f1 and s1 will have this number of points on the other side. So because this is minimum, the payoff of the second player is maximized. So you find the line which has the least number of points on one side and place s2 next to f1 on the other side. So this line will be called the supporting line of f1. Okay? So in 2 dimensions, if you want to play the game for 1 round, the strategy of the second player is easy. And if you remember, because there is only one f1, placing a new facility whose number of users is maximized is exactly the Markov problem. And this is the Markov problem with one existing facility, which I mentioned, if you remember, can be solved in n log n time very easily just by sweeping this line. So that's easy. But what about the solution of P1, the optimal strategy of P1? Now, P1, if he has to protect his own payoff, what he has to do, he has to find a point such that the number of points on one side of the supporting line is maximized. So he has to find a point which has the best supporting line. So find a point f1 such that the supporting line of f1 has the maximum number of users on one side. So that's a well-known notion both in statistics and in geometry. That is called the half-space median or the Tukey median of that point. It's the point such that the number of points that lie on one side of the line is the minimum number of points that lie on one side of the line of all lines passing through it is maximized. And this can be solved in n log cubed n time in a also almost linear. So if I summarize, if I play the discrete Voronoi game in 2 dimensions for 1 round, the second player's move can be done in n log n time, and the first player's move can be done in n log cubed n time. But really, what happens if you play the game for more than 2 rounds, for 2 or more rounds? So in this case, almost nothing is known. Nothing is known about the optimal strategy. Nothing is known about the payoffs. So if you consider for the 2-round game, player 1 places something, player 2 places something, player 1, player 2, 2 rounds. What are worst case payoff bounds? What are algorithms for computing these strategies in 2 dimensions? Nothing is known. Nothing non-trivial is known. Some variants of this problem have been studied. So one variant is to say that I'm going to play the game for 1 round, but player 1 will place k facilities simultaneously, and player 2 will place 1. And here, in this case, this is somehow connected to notions of epsilon nets, and you can get bounds on the payoff. There is another variant of the problem, which is in some sense easier and more extensively studied, is where again you play the game for 1 round, but you place k facilities simultaneously. Player 1 goes places k, player 2 goes places k. So these problems have been studied, and again, but still a lot of things are unknown, but the multi-round game is largely not understood for more than 2 rounds in 2 dimensions. And I just want to mention that all of this is the discrete Voronoi game because I am looking at a discrete set of users and I'm maximizing the number of users served. You can play the game in a continuous area where the goal is to maximize the area of the Voronoi cells that you serve. And Voronoi game really emerged from the continuous domain first. So work of An et al. Introduced this problem, and Cheong et al. Did this problem in 2 dimensions, and that also is studied. So that is Voronoi games, some high-level ideas, some background, some history. Let me now sort of talk about the applications of this problem, in particular, the rabies project that I got involved in recently and how facility location problems appear there. So let me quickly sort of tell you about the group the group here at UPenn, which works on these projects. So the Zoonotic Research Disease Center works on developing algorithms for placing rabies vaccination campaign in Arequipa, Peru. Arequipa is a city in Peru. So rabies is actually still a quite serious problem. There are 59,000 deaths around the world, and about 40% every year. And 40% of them are children under the age of 15. So it is still a very, important disease which needs addressing. So the Pan American Health Organization recommends that dogs be vaccinated at a coverage of 80%. That 80% of the dog in a neighborhood has to be vaccinated for rabies to be eradicated. However, this goal has not been attained in the past 8 years in Arequipa. And Arequipa has a system which is very similar to our system in India, where there are lots of free-roaming dogs in the streets, but many of these dogs actually come to some home at night to stay. So there are free-roaming dogs, but they also have a home. And there are truly free-roaming dogs which don't have a fixed home. So it's a situation which is like similar to our situation we have in India. So how do you place these vaccination tents? So of course, the natural notion would be to, do some k-median or k-center objective and, place the tents in some location which minimizes some objective function based on distances. But we'll soon see that these things often has many practical challenges. Not every site can be placed. They can be hard to get to. One very important practical challenge is that when you measure distance from a user, from a house to a vaccination site, you have to measure the walking distance. You can't just measure the distance as crow flies. So the data that was available was we knew where the houses were, and we knew where the vaccination tents could be possibly placed. So the crow flying distance could be computed. But the walking distance was much harder. So we had to use Google Earth, pay Google some money to get that data, and which was something important that came out of practical considerations. So here is sort of the results from this data. So this is a district in Arequipa, Peru. The left panel here is the mass dog vaccination campaign that was done in 2016. These sites are not optimized. These sites were chosen by the Ministry of Health by some heuristic, visual aid. They place some vaccination sites at various places to balance out things. So this is a human guess based on visual, intuition. We ran the P center and the P median objectives, and the results are in the second and the third panels, the second and the third columns. There are 20 sites in total. So K is 20, P is 20. The area that is served by each of the facilities is marked in different colors. And the intensity of the color is the number of sites that belong to that particular vaccination site. Now we are looking at two characteristics for each of these sites. We want to make sure that no one has to walk too much, right? Because you don't want to walk your dog for too long. So we are looking at the histogram of the distances from each of the houses to the closest vaccination sites. But we also want to make sure that the vaccination sites have somewhat of a balanced workload, that not too many houses are served by a particular vaccination site, because if there's a long line of people waiting with dogs, that can be problematic. So we're also drawing the histogram of the catchment area. The catchment is the number of users that are served by a particular facility. So if you look at the histograms, you see that for the optimized locations, the histograms have a higher peak towards the left, which is natural, which means that more people have to walk less distances, which is what the optimization is supposed to be doing. But there is a little difference. If you look at the P center objective, you see that the P median objective has a larger tail on the right than the P median or P center objective, because the P median maximizes the sum of distances, but it can make a few distances very large. The P center, on the other hand, will minimize the maximum distance. So the maximum won't be too large, but it will tend to make many distances close to the maximum. So the peak is shorter here than here. And we also have an interesting distribution of catchments. So the P median seems to have a more balanced catchment compared to the P center and the human guess. So as I mentioned, the K median distance distribution has a higher peak and a longer tail than that of the K center. And the K median catchment distribution is more balanced. So remember, the objective function that we were minimizing was some distance, sum or maximum of distances. But one new objective came out of this study, which is the catchment sizes. So a natural question that one can try to formulate: is there a way to simultaneously minimize both walking distance and catchment sizes? So that would be an interesting question, which is motivated by a real application. And what would that mean in theory and in algorithms? One thing that again emerged from this discussion was that the K median and the K center both have their benefits. One is maximizing the sum, one is minimizing the sum, the other is minimizing the maximum. So they have their benefits, as you see from the histogram. And is there a way to combine them to find an objective which is somewhere in between? So what we ended up using was a combination of the K median and K center objectives, where we look at the R maximum distances and we minimize the sum of the R maximum distances. So not the maximum distance, but the first maximum, second maximum up to the R maximum, sum them up and minimize that. If you take R to be N, you get the K median problem. If you get R to be 1, you get the K center problem. If you take some intermediate R, it kind of interpolates in between them. And it gives more spatial evenness to do that. So in the paper, the final thing that was used was not exactly this, but something very related. So this was an objective that minimized the distance directly. What in the paper was done was to come up with an objective that minimizes a statistical model for the probability of participation, but it basically did something which interpolates between k-median and k-center objectives. But this gives rise to a host of new problems, right? What you do when you have this kind of optimization problems where you minimize the sum of the top R. Are these problems interesting geometrically? Are these problems interesting algorithmically? All of this, I think, is open, new areas to explore. So recently, we have taught a little bit of the case when R is 2. So you minimize the maximum distance and the second maximum distance. What happens? I think there's very interesting connections to other problems in geometry here. So as I mentioned, this is an example of new problems emerging from applications and the full circle story that I mentioned in the beginning of the talk. So maybe I can stop here. Thank you.
Thank you, Bhashada. That was a really interesting talk on discrete Voronoi games. Are there any questions from the audience? Can we get the mic to sir? Can you please get the mic to sir?
Sinu, I don't know, maybe it's good morning for you right by now.
Yeah, it's 4:30 a.m., but I'm jet lagged, so it's fine.
Sorry about that. Anyway,
No worries, no worries. Yeah.
so I'm not a game theory expert, but I was just thinking, in between you were telling like there are two competing companies trying to put their facilities in order to maximize their commercial gains. What if there are three companies? Means a game between 3 or 4. It can happen like there is Pepsi and there is Coke and there is a third company trying to get the business.
Right.
Is that problem studied or it is similar to the two-game problem?
So the problem makes sense completely, but I think very little is known about these problems. Like, the problem is very natural. There are some very basic results, but I think, it would be interesting to study them and it makes sense. Very little is known.
Thank you. That was my question. So that's possible. That's a new problem, right?
Yeah.
Okay, thank you.
So I have a question.
Oh.
So in the discussion, you assume that the user set, that means is U, that is static. That means through your exploration, cultivation, you assume that your user set is fixed.
Right,
So
right.
what about the situation where your processing is going on, all the algorithms are running, and in the meantime, new users are coming. Right. So is it studied or it's?
That's again a very natural question. I think in the game setting it might not have been studied, but in the coverage setting, the maximum coverage problem, I think finding a region of maximum depth in arrangement of circles for dynamic point sets might have been. But so yeah, very natural. Like points are coming in, points are going out. You still want to maintain the cell which has the maximum depth, right? So those kind of things are looked at in certain contexts, not I think in the game context, but at least in these kind of like more finding cells in arrangement context, I think it has been. I can't really hear the question.
Increase the microphone volume. We'll try to relay the question. We'll try to relay the question.
Sure. Yeah.
Okay. So the positions or the locations of the points in the scenario, they are static in nature. I mean, their positions are not shifting.
Yeah.
I mean, is there any sort of dynamic version or dynamic variant of that? In the sense that the positions or locations are changing over time.
Right. So I think some dynamic versions.
version.
Right. So there are some dynamic versions are studied, but I think in the game setting, probably not yet. But like in the setting where you want to find the cell which has the maximum number of circles overlap, so the max curve. In those settings, there might be something. But yeah, so there's like dynamic data structures and dynamic ways of keeping points are studied in certain settings, but it makes sense, of course, in these problems. I think some things are known, but not, I think, at the game level, I think not much. But yes, it makes sense to study them.
Sorry, many questions. So, final question for me is this. There were two, optimization issues that you talked about the last second of the talk. Icaa came in with right? So is it a sort of since two objective two optimizations are taking place simultaneously, as you talked about, and can it be framed in terms of a multi-objective optimization problem?
You mean in the very end when I talked about the catchment and the sum of distances, that thing?
That's right. That's right.
Yeah, so that one actually I haven't thought about too deeply. I mean, it's just, we encountered that problem in when we're doing this application. So, how whichever way, a formulation makes sense is meaningful, right? I think even there, the formulation of the problem has to be itself done properly. One thing that I was thinking is to put a constraint that the number of facilities, number of users in each facility is not too far away from each other, some kind of bound on each facility will serve, at most this number of users or something. But then, we can probably formulate in some multi-objective problem as well. So there, the question of the formulation is itself part of the question. And it's something that it just came up very recently. It came up. So that's to be thought about.
I really apologize for having to cut short such an engaging discussion. I request our session chair, Professor Bagchi, now to share his views and join us in thanking the guest speaker.
Very interesting talk. Mainly geometric problems. But one question I had was that many of these problems, an approximate solution will be good enough in the applications. You don't need an optimal solution, right? In that case, I feel that you can quickly find an approximate solution using Excel. One way to find a solution quickly is by using Excel. Okay, you can try out different locations and see which one gives good enough solution for your. Is that a sensible thing to do?
Yes, exactly. So in practice, no one does these complicated geometric algorithms. There are these packages which will use some very simple heuristics like local search or try out a bunch of different things and see which works. So in the paper, we actually did something we implemented a heuristic algorithm to solve these problems. We did not implement the provably correct complicated algorithms. There is like a simple local heuristic which was done, and that's what we did. So in practice, exactly, you're right. That's what people do because it's impossible to implement those, n cube log n algorithm, whatever. Yeah.
Thank you, sir.
Yeah.
So I would now request Professor Anup Kumar Sen to felicitate Professor Bagchi. Professor Sen, incidentally, has been guided during his PhD by Professor Bakshi, and later on they have been co-workers and colleagues. So please come on stage. Professor Bhattacharya, thank you so much for joining us. We are now
Thank
having
you.
the felicitation.
Thank you so much.
Please join us in applauding the stalwarts on stage. Bhasharda, we had something planned for you also, but due to online, we are not being able to send it over, but we'll make sure we do it. Thank you, Bhasharda.
That's okay. Thank you so much. Thank you for organizing this. Thank you.
Thank you. Thank you, sir. We do not have a break right now. We'll continue with our next set of talks, and after that, we'll have our break. Please stay in the auditorium. Please sit down and settle down. Discrete algorithms will have one physical presentation and two online presentations. This session will be chaired by Professor Anup Kumar Sen. Now, whoever made the plan of this session and making me the host, there's something very funny happening. All of the dignitaries have been my teachers. So I had the great privilege of introducing all of them. Now, sir has been a very humble and unassuming person, and he requested me to keep his introduction as short as possible, so I'll try my best. Professor Sen has been an academician with over 35 years of teaching and research experience. He is currently a professor in our Department of Computer Science and Engineering at Heritage Institute of Technology, Kolkata. Previously, Professor Sen served as a professor at IIM Calcutta and has held visiting faculty positions at prestigious institutions such as Penn State University, Brunel University, and NJIT. A consistent topper during his academic years, Professor Sen has also received numerous accolades, including national scholarships. His research in combinatorial auctions, workflow modeling, and heuristic or meta-heuristic search techniques has significantly influenced both academia and industry. It's an honor to have him chair this session. Please join me in welcoming Mr. Anup Kumar Sen. Please give him a round of applause. So I'll hand over the session to our next speaker.
Thank you, Icaa. So we will be having three papers in this session. First paper will be presented physically by Professor Nilina Vera of HIT. And the paper has been titled as Dilution with Digital Microfluidic Biochips, Unbalanced Split Error Correction with CMOP. The co-authors are Professor Bhargav P. Bhattacharya, ISI, and Professor Subhashis Majumdar, HIT. I can see Nilina, but I think you can start. So you have 15 minutes for your presentation.
Yes, sir.
Then
Just give me 15 minutes, let me start. Sir, may I start? Hopefully I am audible to all of you. Good afternoon, respected professors, dear colleagues and students. Myself, Dr. Nilina Bera. Today I am going to present dilution with digital microfluidic biochip, unbalanced split error correction with SIMA. And I am fortunate to have Professor Dr. Subhashis Majumdar and Professor Dr. Bhargav D. Bhattacharya as my research guides, and they are my co-authors too. So let's start. Then what is digital microfluidics? It utilizes the technology of controlling small amount of fluids on chip. Here the control means transporting, mixing, merging, splitting, dispensing of droplets. Here the droplets means small amount of fluid, that means 10 to the power minus 9 in scale. That means 1 unit volume droplet. So let's have a look next. So our table of content, we have CMOS, the brief definition of the CMOS algorithm. Then unbalanced split errors. Then equivalence of single and multiple split errors. Then error correction of the CMOS target CF. Then correcting the effects of multiple split errors. And obviously at the end, conclusion, future direction and references. Now, let's have a look at what is mixing and splitting of droplets. Now we have got 3-to-1 electrodes located on line. Now we have got 2 droplets located on these 2 electrodes, and we have got actuation sequence 1, 0, 1. Here 1 means on, the electrode is on, and 0 means the electrode, the middle electrode is off. And these 2 droplets, they have got concentration factor C1 and C2. C1 not equal to C2. Then our goal is to merge these 2 droplets into a bigger droplet of size 2x. Now 1x is the 1 unit volume and 2x is the bigger one. So we have to change the actuation sequence 0, 1, 0. And this one is a high electron. It is kind of like pulling this smaller droplet towards it. That means we are merging to make a bigger droplet of size 2x. Now splitting. Now we are changing back the actuation sequence to 1, 0, 1. So this one, the high electron, they are basically pulling forces, okay, generated from the higher side. These 2 high electron, this is the splitting this 2x unit volume of droplet. So we are coming back into 2 1x droplet. But the difference is the concentration factor. Here the concentration factor is different. This one is C1 into 1x plus C2 into 1x by 1x plus 1x. And these 2 electrodes, they have got a different concentration factors. Next, let's have a look at how to disperse and split droplets. We are going towards the unbalanced split error. So what is a balanced split? This is the reservoir. It stores the droplet. When we are pinching out the reservoir, if it is okay, no problem, then it is pinching 1x of droplet. So 2 1x droplet, it's a balanced split. But suppose the reservoir is pinching out 1 extra droplet of size simply epsilon. This is the extra droplet is called the volumetric error or the volume error. So this one is the size 1x plus epsilon. And if this is a 1x plus epsilon, obviously we have to balance it out 1x minus epsilon. To make it cutting out this epsilon plus epsilon minus epsilon, we are getting 2x. So this one is called unbalanced split. And our CMOP algorithm, we have to go analyzing. So obviously the unbalanced split errors, okay, on the CMOP target. Let's have a look what is CMOP. CMOP is simulation procedure for optimizing sample dilution. So CMOP takes a single user input. Let's have a look what is X. X is a maximum number of 1:1, that means balance, mixed split steps. So let's see X equal to 4. That means 2 to the power 4 equal to 16. So we have got from 1 to 15 numerator, okay? And with the upper the denominator 16. So let's have a look at the CMOP 3. Sorry for that. Yes. So this one is a CMOP 3. We can generate 33 unique sequences from 4, 1:1 mixed split steps. So very first one, the first node of the tree, we have got 4 steps. That means 4 levels. So very first step 1, we have got the buffer 0, sample 2 to the power 4, 16. So we have got the first intermediate 8, 0 plus 16 by 8. So 0, 8, 16. So CMOP algorithm over here, we are carrying forward all the target numerator generated. So then we are branching out. Left child, right child. Left child, we have got 0, 8. So getting the new C intermediate 4. Right child, 8 and 16, we are getting new C intermediate 12. So we have got 4 concentration factors over there. 0, 4, 8, 16, and then 0, 8, 12, 16. Now step 3. So we are branching out into 3. Okay, 3 nodes. Over there, the left hand side of the tree and the right hand side of the tree, parallel, we are basically moving forward. So 3 nodes over here, 0, 4, 2, 4, 8, 6, 4, 6, 4, 16, 10. That's the left side, right side, 0, 12, 6, 8, 12, 10, and then 12, 16, 14. So we have got altogether 0, 2, 4, 8, 16. In this way, we are progressing. Now the leftmost node over here in the CMOP tree, now we are further branching out. Maximum we have got 4 steps. So we are in the step 4. So here we have got 4 nodes coming. 0, 2, 1, 2, 4, 3, 2, 8, 5, then 2, 16, 9. Now the interesting situation over here, just check, we are basically generating 5 upon 16 in 4 different ways. That means 4 unique CMOP sequences. So why we need all this? I'm sorry. There is a concept of optimization. Optimization of what? Sample, buffer, waste. So these are the 3 CMOP sequences. So over here, CMOP sequence 1, we have got sample, 1 droplet, buffer, 3 droplet, waste, 2 droplet. So creating the CMOP sequences to generate the target 5 upon 16, we need 1 sample, 3 buffer, and 2 waste got generated as an output. Now sequence 2, we have got 2 sample, 3 buffer, and 3 waste. And sequence 3, all sample, buffer, waste, we have got 2 droplet each. So if the user wants to select optimum sample, so sequence 1 is the best. Select optimum buffer, sequence 3 is the best. Select optimum waste, either sequence 1 or sequence 3 is the best. Now, we are here in the error propagation of the CMOP target. So let's have 2 to the power 5, that means 5 steps. So 2 to the power 5 is equal to 32, and our goal is to achieve the target 9. 9 after 32, and there is a 5% volume error. 5% means 0.05, and this is the positive. Volume error can be positive, negative. Okay, so this is basically the CMOP dilution tree to generate 9 upon 32. So we are starting with buffer and sample, and we have got 5 steps over there. Just check in the step 3, the concentration factor C3, we have got a waste. And if there is a waste, we can apply the volume error on the higher step. Okay, if it's a step 3, so next step, step 4, we can apply waste. And the volume error we are signifying by epsilon. Here the epsilon is plus 5. Okay, so 1 plus epsilon. If it is the waste is 1 plus epsilon, we are propagating. So the volume of this waste is 1 minus epsilon because we have to balance out. Okay? And this way we are progressing. And over here, instead of generating 9 upon 32, we are generating 8.93 into 7. That is our resultant target CA. So there is a concept of deviation. We are calculating deviation. What is that? Our desired target 9 and our actual target that is generated. So 9 minus 8.93827, we are getting 0.06173. There is a threshold. Threshold is if the deviation is within minus 0.5 to plus 0.5. That means we can ignore the error. This is an error, but this deviation, this I think we can bypass. This really we cannot consider this as an error. Okay, so this one is we call it as a non-critical deviation, so non-critical error. And there is also a concept of critical error, and critical error should be corrected. So let's see. So this one is basically 2 to the power 9, that is 512. So there's a target is 1 by 512 and then 511 by 512. So this one CT and its complement. And it has got 8 waste droplet. So over here, out of 9 steps, we have got waste in 8 steps. So this one is for 1 by 512. This dilation 3. And this one, this dilation graph is for 511 by 512. Over here, altogether wasted step. What is the difference? Here, the buffer. The buffer droplet is 9. Sample is just 1 droplet. The complement buffer droplet is 1. Sample is obviously 9. Okay, so let's see. Now, our goal is to apply waste. Okay, 1 step at a time. And here we are applying there. We are applying plus 10% of volumeter. So how we are applying? Just have a look. So first, suppose step 1, there is a waste. So this waste we can apply the next step, step 2. Another one, suppose step 4. Step 4 has got a waste. We are applying the error on step 5. Same way, step 8 has got a waste and we apply error on the 9th step. Okay, this way we are applying error, volumetric split error plus 10% on individual step. As I told you, 1 step at a time. And we are getting the deviation. All throughout we are getting non-critical deviation. That means they are within the range. Let's see, the range is minus 5 to plus 5. So over here, this one another observation, all these deviations of the same value, but they are opposite in signs. Yeah. Okay. So this one is another example of 96 by 256. So 256 is to the power 8. That means 8 steps. So there, this particular target, we are applying 3%, 5%, 7%, and 10% volume error. And just to check, for 3% error, we are having non-critical. And for 5, 7, 10, we are having critical. Just check this deviation is 95.52709. It is within the range. Okay. And this one is exceeding the range. 1.0, 1.5, 2.0. Those are basically the critical error range. This one is the equivalence of single and multiple split error. There is an observation. 2 unbalanced split error, epsilon 1 and epsilon 2, is said to be equivalent if they result in the same final CM when either error is present. Let's have a look at this schema. This is an important one. Just check over here, we have got 4 targets. With this one, with 8 steps, 2 target with 8 steps, and 2 target with 9 steps. This one, just an example, 59 upon 256. It has got 2 ways on step 4 and 6. And we are applying multiple errors. From step 4, we are applying positive 10% volume error, and on step 6, we are applying negative 10% volume error. In contrast, we have picked up just step 6 and we have applied just 1 single error. So it's a plus 10% volume error. And this is the interesting result. This one is the final CF error, the deviation. Deviation is same as the multiple split and the single split. And this is like happening in all these targets. Okay, we have just picked up the couple of bunch of zero targets, and the deviation is same. This proves that the single split error is equivalent to multiple split error. Okay, this is one of the observations. Then we have got cancellation of the unbalanced split error. Yes. To reach the target, suppose 513 upon 512, 512 to the power 9, and we have got 6 waste over here. Waste is there, S1, S2, S3, S4. Waste is there, waste is not there, S5 and S6, waste is there, S7, S8. And whatever you are like applying, the volumetric split error again, 10% plus and minus, and if we add this up and divide it by 2, we are reaching the our desired target. This is the cancellation of the split errors. Then this is the multiple performance of plus 3% volume error on obviously on the 4 steps. Just check step 1, step 2, sorry. S2, S4, S8 and S10. S2 we are getting with 3% volume error, we are getting a critical. So it is basically exceeding 5 deviation. Yes. Sir, can you please give me one minute? And then for S4, S8 and S10 we are getting non-critical error. Over here, multiple step performance, we are basically applying the multiple step error in all these steps. So over here, all the trial multiple steps. Step 2, step 4, step 8, and step 10. We are having errors. These are basically okay. That means non-critical errors. Conclusion and the feature correction. We have analyzed the impact of volumetric split error on dilution assays performed using the SIMO-parameter. Our analysis led to a fault tolerance technique that guarantees that the target scale remains accurate even when multiple split errors are present. Then critical split errors are corrected to ensure error-free dilution. The impact of cumulative multiple split error, cumulative means this one. This one is the cumulative split error. So let's almost at that. The impact of cumulative multiple errors on target CF is obviously investigated and how they can be neutralized. The study establishes the capability of SIMO algorithm to achieving error-free dilution. Sorry for my cough. So I have done. So this is basically the references, the papers we have analyzed, and I've already got a question. Thank you,
Yes.
Yes, question, please.
The errors are being considered at multiple points. Well, I think that only one error that happened, and that we were so okay, can I approximate that with a single speed error? Is that a part?
Yes, that's basically one of
The other idea is if you have introduced error in a multi-step, can you introduce that erratic twist again so that
So I have a very basic question. What is the use of a digital microfluidic biopsy? They available now?
Yes, sir. They are available. What is the purpose? Purpose is for the very fundamental and very good question. So digital microfluidic biopsy, we are doing research. I will shoot for medical and healthcare purposes. Over there, we have checked in the papers, lot of papers, they talk about blood, infant's blood, very rare. And there suppose one infant just after the birth, the infant has got some problem. So they have to like do some analysis or the blood circle. And blood circle means one droplet we're talking about 10 to the power minus 9 in the scale. But the infant's blood, the real blood is really big. Okay, so one drop of blood is really important, very important. So we have to perform all the analysis with digital microfluidic. All the blood we have to dilute with the KCl solution. 0.5 mole of KCl solution, that is the buffer. So digitally, we have to like put the blood, and the researcher, basically the chemist like has got to reach a set of target. And that target solution with the blood sample diluted blood, we can reach that target and then we can analyze what problem the infant is facing.
These sheets are available now. In use.
Yes, even they are available on paper. On the paper, you can like draw the digital microfluidic or the electrode. And they can be obviously tracked by the CAD computer aided design from the computer. You can like track it.
Okay, thank you.
I can answer that. So the idea was like all the pathological tests of yours and mine will be done by digital microfluidics. You will take just one drop of blood and do the whole thing. It has not come to that level, but maybe someday.
This paper is online. Here is editor. On the characterization of Mullerian splitting P matrices. To be presented by Shivaji Gunjal.
Yes. Good afternoon, sir. Am I audible? Hello. Am I audible?
Yes, Your Honor.
Yes. Thank you so much, sir, for the confirmation. So I take this opportunity to thank the organizer for this chance to present my work. So basically, I'm a person from mathematics. So I was hearing all the computer scientists from yesterday.
You have PPT uploaded?
Yeah, I have uploaded the PPT. So I'll start sharing my presentation.
Please share your PPT, then you can talk because you are seen upstairs.
Yeah.
The upper layer you are seen, right? So you can upload your PPT and start talking. Yes, please. Sorry to interrupt
Yeah.
you. Continue.
Yeah, yes, sir. I hope it is visible now.
Yes. Yes.
Yes. So title of my presentation is on the characterization of Eulerian ES splitting P matroids. So this matroids has connections with graphs. So in the brief, I'll be starting with the connections, and then later I'll go to the technical theorems which are proved by us. So I'm Professor Sachin Gunjal from Department of Mathematics and Statistics, MIT World Peace University, Pune, Maharashtra. So a matroid M is an order pair E, comma script I, consisting of finite set E and the collection I, which is subsets of E, satisfying three conditions. So first is empty set must be member of script I. Second, if I is member of script I and J is subset of I, then J is also member of script I. And third condition is if there are sets I1 and I2 which are there in I with cardinality of I1 less than cardinality of I2, then there is an element E of I2 minus I1 such that I1 union E is a member of script I. So this set E is called ground set, and the members of I are called independent sets of matroid M. The minimal dependent set in M is called circuit of M, and the set of circuits of M is denoted by script C of M. A maximal dependent set is called a basis of M. We denote that set by script I of M, and the set of bases by B of M. So there are two ways to form a matroid. So first is by matrix. So let E be the set of column labels of M cross N matrix A over a field F, and let I be a set of subset X of E for which multiset of column label by X is a set, and it is linearly independent in the vector space V of M comma F. So in this case, this script E comma I becomes a matroid, and it is denoted by M of A, and it is called as vector matroid of matrix A. So and the other one is by graphs. So we can see that there is a graph and matrix for that graph, vertex edge incident matrix for that graph. So here we can see that this E1, E4 are parallel edges. So from the matrix also we can see that 1 and 4 are parallel. This edge E2, E4, E5 forms a circuit in graph G. Then this column number 2, column number 4, and column number 5, their sum is 0. So that forms a circuit in matroid M. So this is the relation between a graph G and a matroid M. So the graph derived from this graph G is called cycle matroid. So there are certain operations introduced by Fleischner and Slater on a graph G, which we were interested. So we have graph G, and this figure B gives the splitting of a vertex. So vertex V is splitted like this. So that operation is called splitting operation. Then adding an element Z between those splitted vertices is called element splitting operation. And adding a new edge, say gamma, from B to V2 in the element splitting is called as line splitting operation. So these are certain operations from graph, and which are taken into matroid by this author. So Raghunathan et al. Extended this splitting operation of graphs to binary matroids and characterize Eulerian binary matroids. And later Shikare generalized that n element splitting operation from graphs to binary matroid, and Azanchiller extended n line splitting operation from graphs to binary matroid. So these papers are mentioned here. What we have done is we have extended this operation to P matroids. So by P matroid, we mean a matroid that is representable over the field GFP. Okay, from binary, we moved on to field GFP, and we check all the circuits, bases, and connectivity result for these matroids. So it is known that this ES splitting matroid MEAB is not binary, is not Eulerian in case of binary matroid. But for P matroid, we have given a characterization. So we have provided a necessary and sufficient condition for ES splitting P matroid to be Eulerian. So I'll start with the definition of splitting operation. So for a matroid M, which is representable by a matrix A, so splitting operation is augmenting or appending an extra row to that matrix A, which has coordinate equal to 1. Okay, we'll fix the position A comma B, and corresponding to that position, let us append 1, 1, and all other places are 0. So we have a matrix A suffix AB, and that matrix is called, matroid is called MAB, and it is called splitting operation. Now, the second operation is element splitting operation, where we have a matrix A and a corresponding matroid M. So let us do splitting operation first. That means appending an extra row corresponding to position AB, we have 1, 1, and at rest of the position there is 0. And here we'll add one more column labeled as Z, okay, which takes coordinate equal to 1 and rest of the entries 0. So this matrix obtained by this operation is called element splitting operation. And next is the ES splitting operation. So where we have a matrix A, then splitting operation on that matrix A, so which is done by adjoining one extra row, and then we'll attach Z, that is element splitting operation. And then we attach one more column labeled as gamma, which is subtraction of E minus Z. Okay, so that new matroid is called ES splitting matroid, and that operation is called ES splitting operation. So as a quick example, I'll take you through this. So we have a matroid M given by matrix A having column label 1 to 8. And let us fix the position 1, 4. So we can see that there is appended row where at position 1 and 4 there is 1, 1. Okay. And then let us adjoin one column labeled as 9. We call it as Z. So where we have everything 0 and at last entry there is 1. And then this column number 10, we call it as gamma, which is subtraction of 4, 9, 4 and 9. So that becomes the ES splitting matroid AE14. So we need some technical definition for a matroid. So we have a column label, say U1 to UL. CK be the column labels U1 to UL. For some positive integers K and L, if CK intersection AB is 2, and we let us assume that they are U1 is equal to A and U2 is equal to B. If there are some non-zero constants, A1K, A2K, ALK in prime field GFP, such that this summation AIK UI is 0 mod P, and the sum of the coefficient A1K plus A2K is 0 mod P, then this circuit CK is called P circuit. However, if this intersection is 1, or if that intersection is 2 and sum of the coefficient is not 0 mod P, then we call that circuit as NP circuit of a matroid M. We denote the collection of circuits which are P circuit or its intersection with AB is phi by C naught. Let us consider a subset E of the type C union I, where C is column label U1 to UL is an NP circuit of M, and it is disjoint from independent set I having column label V1 to Vk, and AB is subset of C union I. The C union I is called P dependent set if we have non-zero constants alpha 1 to alpha L and beta 1 to beta K, such that this linear sum is 0 mod P. Moreover, the coefficient of A and coefficient of B is 0 mod P. So such a set is called P dependent set. So with this definition, we have characterized the circuits of newly obtained matroid MEAB in terms of circuits of matroid M. So C0 to C8, and there is this additional circuit EZ gamma. So because of this EZ gamma, that is 3-element circuit, this ES splitting matroid is not a bipartite matroid. So the circuits of M, circuits of splitting matroid M14, and the circuits of ES splitting matroid are listed from C0 to C8 in this table. And we have also characterized bases of newly obtained matroid MEAB in terms of basis of M. So this script B0 to B5 are types of bases for the matroid MEAB in terms of circuits of original matroid M. Then we have defined a rank function for that matroid MEAB in terms of rank function of original matroid M. So it can be observed that rank is sometimes increased by 1 and sometimes it is increased by 2 for that particular set X. So next we have obtained some result related to connectivity. So let me define connectivity of a matroid first. So let M be a matroid having ground set E and let K be the positive integer. The K separation of a matroid M is a partition S comma T of ground set E such that the cardinality of S and T is greater or equal K and rank S plus rank T minus rank of M is less than K. So for an integer n greater or equal. Sorry.
3 minutes left.
Okay. So we say that M is n connected if M has no K separation from K running from 1 to n minus 1. So we have derived the lemma if M is connected P matroid, then corresponding ES splitting matroid MEAB is also connected. We have derived this lemma for 3 connected as well. So this is our main result of this paper. So it is a characterization of Eulerian ES splitting P matroid. So let us define what is Eulerian matroid. So for Eulerian matroid M on ground set E, if there exists a collection of disjoint circuits C1 to Ck such that union of all of them is the ground set E. Such a matroid is called Eulerian matroid. So we have the theorem, let M be a P matroid with P greater than 2 and AB are the elements of E of M, then ES splitting matroid MEAB is Eulerian if and only if there exists a circuit collection CNP to CK such that their union is E of M, where there is one common element between CNP and C1, that is B. So this has been verified for the example which I have stated above by taking A as 1, B and E as 4. Then we can see that 4 is common element between them. And this is the circuit decomposition. So we have also characterized, we have also given a condition to obtain Hamiltonian matroid. So Hamiltonian matroid is a matroid where it has a circuit of size rank M plus 1. So let M be a P matroid containing an NP
1
circuit
minute
CN
left.
of
1
size
minute
Rm plus. Yeah. I'll finish it. So let M be a P matroid containing an NP circuit CNP of size Rm plus 1. Then MEAB is also Hamiltonian. In that case, these two are the Hamiltonian circuits. So this work is carried out in collaboration with Uday Jagdale, Prashant Malhotkar, MM Shikare, and B.N. Wafare. So these are certain references which I have listed. So, yeah. Okay. So our current project is related to information theory and matroid theory. That is connection between information theory, that is algebraic coding theory and matroid theory. So I am done with my side. Yes, thank you.
Can you hear me?
Yeah, yes, I can hear you.
Thank you so much. So let me see whether there are questions. The accepted definition of matroid have any applications in optimization also?
Yeah. See, binary linear codes that is being used by computer scientists, that parity check matrix, Hamming distances, they are same as binary matroid. The 1-0 matrix and linear codes are equivalent. So the operation which I'm doing on matroid can be taken into binary linear codes.
For normal matroids, the greedy algorithm works if and only if it's a matroid.
Which greedy algorithm, no?
They work if
Yeah,
and only-
greedy algorithm is also defined for matroid.
They will work if and only if the structure is a matroid. Is there similar characterization for the extended definition also?
No, sir, I did not study greedy algorithm, but I have heard about greedy algorithm.
Any other questions? There are no other questions. Thank you so much once again.
Yeah, thank you, sir.
Thank you, Sachin. Our next paper is also online. Is approximability of edge vertex domination in unit disk graphs, and represented by S. Vishwanath Reddy, and the co-authors are Manjana V. And the co-author is Manjana V. Your audio is mute. Can't hear you.
Am I audible now?
Now we are audible. Yes.
Yeah.
Thank
Good afternoon, everyone. This is Vishwanath R. Singh Reddy. Title of the paper is Approximality of Edge Vertex Dominating Set in Unit Disk Graph. It is co-authored by Manjana Basappa, NIT Surat. This is the organization of the talk. I will discuss two solutions for this problem, which shows that it admits a p-test and a simple linear time 5-factor approximation algorithm. A graph is said to be intersection graph if it is resultant from the geometric objects, and if these are and geometric objects has a vertices, and if there is an edge between these objects if they intersect. If those objects are of disk or circles of equal radius and it is equal to 1, then that intersection graph is called unit disk graph. Consider here we have disk. So these disks are treated like vertices. Centers of the disk are treated like vertices, and there will be an edge if they intersect. The red color one is an unit disk graph here. This is a unit disk graph. Some of the properties are it is a planar graph, and it can have degree of a vertex not more than 5 or 6. A dominating set is like of a graph is like subset of vertices such that every vertex in a graph is either in the dominating set or adjacent to the vertex in the dominating set. Finding the minimum dominating set is the problem is referred like MDS problem. Consider this graph. These red color vertices are referred like dominating set. A graph can have a many variations of the dominating set. Here, two vertices, red color vertices, are the dominating set because all the vertices of the graph either in the dominating set or adjacent to the dominating set. This is another variant of the dominating set, where connected dominating set is also referred like, where because the vertices in the dominating set are connected. A special type of dominating set we have worked, that is edge vertex dominating set. It is introduced by Peter. The edge vertex dominating set is here, edges are going to dominate vertices. A vertex is said to be EV dominated if it is incident to that edge or incident to the edges that are adjacent to the edge in the EVDS. Consider graph here. If I consider edge A into the EVDS, then all the vertices here are dominated because either all the vertices are either incident to A or they are adjacent to the edges which are incident to A. The edge vertex dominating set in unit disk graph, we have results, and this many dominating set problems have the applications in the networks. A specific example application for this edge vertex dominating set is, consider this is a network of an organization where the boxes, the nodes are referred, and the edges, if they are the connections. And consider these nodes are in the watchful area, means they are under surveillance. Links may go outside of the watchful area. These applications could be in the form like introductory context and network designer context. Like it's like intruder, if you want to get the control over this network, he can find minimum number of the edges which are outside of the watchful area to get the access to those network to the network. Why? Because if he get the access to this blue link, he can get the control over these two nodes. With the help of these two nodes, he can get the control over the adjacent nodes of that. Like that, these links are referred like crucial links. So in networks designer's point of view, in a network, crucial links has to be identified and establishing the encryption methodology so that it could be more secure. But finding the crucial links is cost effective. So finding the minimum number of the crucial links can be given by edge vertex dominating set of the graph. Related edge vertex domination is introduced by Peter. It is NP complete for the general graph and even when restricted to bipartite graphs. Minimum dominating set in UDG is NP her. And other dominating models such as Roman dominating set, minimum layers dominating set, vertex edge dominating set are proven to be NP complete. And for all these dominating sets related to UDG, they propose p-tasses based on the M-subgroup collection. We also proposed a similar method. So first, I'm discussing polynomial time approximation scheme. It is M-separated. We are going to find the M-separated subsets of the given graph. Like this M-separated collection is going to divide the graph into disjoint sets, disjoint graph. Those are edge-induced subgraph. So it is like if I get the EVDS of those disjoint sets, the union of that will be empty. For the EVDS problem, the parameter m will be 4. It is because an edge chosen in the one subset should not interfere with the edge vertices in the other subset. To make that, the distance between these subsets should be at least 4. And the algorithm is very simple. Like we need to partition the graph into subset graphs, and we will find the maximum matching, which will give the EVDS of the local graph. And we will show some like boundings of how this maximum matching will give the p-test for the EVDS problem. Consider this graph. This graph is graph S is divided into five subsets. Like if I choose an edge here, it will not influence the vertex in this graph. It will be it will choose up to here. If we choose an edge here, it will go up to here. And there will be some more space because they should not be influenced. And this strategy follows that we will get the enlarged set of the given subset. So here we are going to find two subsets. One is S1, edge-induced subgraph, and we will get the enlarged sets of that. When we do the union of these enlarged sets, it will give the complete edge set of the graph. So since these sets are disjoint, the optimal EVDS of the collection of the edges in the optimal EVDS of these sets is at most optimal EVDS of the whole graph. That is, this lemma states that the 4 separated collection of the subsets of the edges will give the lower bound for the cardinality of the EVDS. This helps us to give the p-test. Hence, we can approximate EVDS if there is able to, if we are able to enlarge the subsets from SI to QI. SI is the subset which we have chosen, and we are enlarging this subset, like extending to the next subset, that is QI. Such subset, if QI, such a way that EVDS expands to bounded locally and dominate every vertex globally. So whatever the expanded sets are there, if we collect the edge vertex dominating sort of those expanded sets, it will dominate every vertex of the graph. So hence we have this lemma, given graph S1, which is 4 separated collection, and Q1, Q2, Qk are the collection of subsets which are enlarged, and Si should be the subset of Qi. It is extension of the Si. And if there is a row which is greater than or equal to 1, here row is 1 plus epsilon as a p-test for a p-test, and such that if there exists a row such that EVDS of enlarged set is row times the EVDS of the basic set, which one we choose an initially, S1, holds for all the k, then union of the EVDS of this enlarged sets is an edge vertex dominating set. Then it will give the row approximation for the minimum EVDS of the graph. Okay, this will, as long as this condition is whole, the collection of all the union of these enlarged sets will give the EVDS that will give the row approximation of the minimum EVDS of the total graph. And whatever the edges we collect in this QI, that will dominate every vertex of the whole graph. So it follows from the lemma 1. We know that the EVDS optimally collection of edges in the optimal EVDS of SI is at most optimal EVDS of the whole graph. So which will give the row time approximation of the EVDS of opt. There is a simple variation in the edge. Generally, we have vertex neighborhood. We use the concept of edge neighborhood. Edge neighborhood, I am suffixing it is with E to show edge vertex. It's similar to general neighborhood in the graph. We have open and closed neighborhood. Here, edge neighborhood 0 is an edge itself. And edge neighborhood one distance is, it's like the set here and adjacent edges of this above set. Like E is there and adjacent edges of the E. And if we go for N2, it is this set and adjacent vertices of this, the edges in this one. Like E, these first 4 edges are the part of the previous one, N1, and adjacent of these one is like E4 and E5. We can have edge neighborhood of the set is similar like here. N2 we have N1 is a set. Like that here I am denoting E1 as a set of edges. Edge neighborhood of set of edges is adjacent to all the edges in that graph. So this edge neighborhood helps me to find the like edge induced subgraph SI and enlarging one. So how I'm going to find the subset? I told like we will find the subsets and we will extend those to the enlarged subsets. So we are going to find, we choose an edge E and find the rth neighborhood of that E, starting with 0th neighborhood is E itself. And we will do this thing until this condition is false. When this condition is false means whatever the initial condition we chosen for the row approximation, that will be valid. So like that, we will find the subsets of the given graph. So here, this one R plus 4 is a 4th neighborhood. From R, 4th neighborhood. The right hand side set will give the cardinality of the like set Si, and left hand side will be the cardinality of enlarged set Qi. Okay, let R1 be the smallest which violates the condition. I will make it as S1 and enlarged set as Q1. Then I will choose another set in the remaining edges. Like that, I will repeat until there are no more edges in the given graph. And the EVDS of these can be found by finding the maximum matching M for the graph induced by the edges of the rth neighborhood of the E. So we can easily prove that maximum matching of the graph, for a set n that neighborhood R like Si, it will be gives the EVDS of the graph. And yeah, G prime is a UDC induced by the edges of the NER, and M is the maximum matching. Then it will be bounded by R square. Here R is the rth neighborhood we are looking, right? It is because it will be bounded because we are considering the unit disk graph. If we are considering the unit disk graph, there will be an edge between the vertices if the distance is at most 1. So it will bound the area. It is like a
3 minutes
polynomial.
left.
Sir?
3 minutes left.
Okay, thank you. Yeah, hence we have the theorem that we here in this theorem we showed that there exists a like R such that it will be it can be enlarged. It means that whatever the bounding condition for R1 is 1 by epsilon into log 1 by epsilon. Yeah, this EVDS will be EVDS of the QI can be computed polynomial time. It is because of the unit disk graph. The area is covered at most R square, disk of the radius R plus 2 whole square area. So it collection of the, since we are choosing edges such that union of the EVDS of those enlarged sets will give the edge vertex dominating set of the given graph. Hence we have the following corollary, and this is the PEAT as we have. And 5-factor approximation is very simple. Like given graph, unit disk graph, we consider in the 2-dimensional plane, and we will tessellate with the regular hexagons like this. Each regular hexagon of side of 1 by 2, and so if any 2 vertices are in this hexagon, they will have an edge between them. Consider this unit disk graph. This is a mega cell, which one tessellation of hexagons. This graph can be kept like this. So my algorithm is very simple. I choose an edge which is whose endpoints are in the different hexagons. Then that edge is going to dominate all the vertices in those two hexagons. I will remove those vertices and that edge. Then the remaining part, I will repeat the same thing. So my algorithm may choose these 5 edges, whereas optimal solution could have this edge E. So if the graph is very large side, we can have this type of arrangement of the mega cells. So this is the algorithm. We chooses an edge and we will mark the vertices which are there in the 2 hexagons whose endpoints are in the different hexagons. So it will be done in the linear time. So we showed that EVDS admits p-task based on the local neighborhood based scheme and 5-factor approximation algorithm which takes R of n plus n where m is the coordinate of vertices and edges. Yeah. And whatever the 5-factor approximation algorithm we give, it is
1 minute
faster.
left.
Yeah, it is faster, but it requires geometric representation. But whatever the p-task we propose, it does not require geometric representation. Hence, it makes the algorithms more robust. As a future scope, we believe that EVDS in the unit graph admits NP, like it is NP-hard. And is there any better constant factor better than 5 or sub-quadratic running time of the algorithm? These are the references. Thank you for your attention.
Thank you.
Thank you.
Any questions?
Can you please get the mic? There's a question from the audience.
Wait for a minute.
Saxena sir, did you have the microphone?
What?
So you can ask the question and we'll relay it. There was a question.
I did not hear it.
Oh, no question, sir.
Okay, I see. Sure.
What he said is that the application is a network, right? The network examination.
I could not hear it properly.
Yes, the application was in it.
So let us try this.
Yeah, so what you said is that edge cortex domination problem, the application is in networking.
Yeah,
What
it is networking. It has other applications like where facility location problems, where we are looking for the facilities are like edges. It is like park, if you consider the park as an edge, and vertices are the nearby locations. Like that we can model. It has other applications, but for the motivation, we consider in the context of network, that specific example.
what does the edge mean in facility location? Can you please repeat?
Edge means like if we consider a park, we cannot model like park as a single vertex at a single location. It can have multiple entry points.
Okay, park. Okay.
Yeah.
Now, what about thinking the edges as roads and if you hold one road in your set, then adjoining roads are monitored or something. I mean, I don't know. Can it have a variation of
Yes, sir. Yes, sir.
cardinality problem with this one?
Yes, sir. It has many applications like other like mining areas. Like if you consider Australia, many mining locations are there. If you want to place some base station to provide the services to those missionaries, we can model that also.
Okay, thank you.
Thank you, sir. Well, so that sort of brings us to the end of this session.
Thank you so much.
Thank you, sir.
Thank you.
We have had multiple enlightening talks ranging from CMOPs and Eulerian matroids and graph theory. So that concludes this session, and now I would request Professor Sen to share his views and wrap up the session.
I don't know what views are. It was from me. Right. The only views I have, but gradually I find that the audience the auditorium is gradually getting empty. That's the views I have. I don't know what will happen for the next session which starts about 10. So I'm a little worried about that.
So we'll try to get back the audience. So with that, I would request my guide during my post-graduation days, sir, please. The HOD of Computer Science and Engineering, Professor Dr. Shubhashish Majumdar, to felicitate Professor Sen. Give them both a big round of applause.
Yeah, it's an honor to felicitate Professor Shen because he also, like as a retro Shen, he had been the examiner of my MTech thesis. Okay, that's the first time I met him. Okay, thank you.
Okay, so we are running a little late, about 20 minutes late. So we'll take a short 10 minutes break now and reconvene back in 10 minutes. We'll take a 10 minutes coffee break. We have 4 more papers. Okay, so we'll do a 15 minutes break and 4:30. Okay, so we'll reassemble at 4:30. We have 4 more papers to go. Sorry, 4 online papers and 1 physical presentation.
বাউলের গান আর পুজোর করছে তো আমি ভাবলাম যে এরা তো সাংঘাতিক শ্রোতা ভেতরে গিয়ে শুনি বাউলতে যেন পারফর্ম করে না আমার মনে হয় এখানে না এলে ক্যাজুয়ালিটি ফেলে দেবো না এলে কি ওরা করতে হবে
ছয় সাত আট নয় 10 11 চারটে বাদ দিয়েও একজনের পাবলিক ইঞ্জিনিয়ারিং এর উপর 40 জন থাকার আসবে না তো ভিডিও অন আমার ক্যামেরাটা লাগানো আমার লাইটিং ক্যামেরা
Welcome back, everyone. Please settle down. We'll start the next session. Please settle down.
Oh, sorry. Very sorry.
All right, so we'll start the last technical session for the day. Some of the models to be discussed in this session have probably taken more time to build than the break that we have taken right now. So all these papers will be from track B, machine learning. And to chair this session, I again have the great pleasure of introducing one of my teachers, Dr. Partho Boshu Chaudhary. Dr. Partho Boshu Chaudhary is an associate professor and the chair of the School of Mathematical and Computational Sciences at the Indian Association for the Cultivation of Science, Kolkata. He did his bachelor's degree from IIST Shibpur, master's from Louisiana State University, and PhD from Jadavpur University. He also did his postdoctoral research from Queen's University, Belfast. His areas of interest are machine learning, that's the track we're discussing, natural language processing, biomedical image analysis, and social network analysis. He has been awarded an Indo-Swedish joint project in collaboration with Uppsala University in 2021. He has been publishing papers with his collaborators from University of Glasgow, University College London, and Jadavpur University at prestigious conferences and journals. Please join me in welcoming Partho to chair this session. Partho, over to you. Yeah.
So I can see overall 5 papers are here in this session. So first one is going to be a physical presentation and rest are online presentations. So we can call upon the first presenter. Name is Oni Diptopal, and the name of the paper is Artificial Intelligence Driven Monitoring System for Detecting People Using Mobile Phones in Restricted Zones. So may I have Oni Diptopal over here for the presentation? All right, great.
So, a very good afternoon to the chairperson and all the present today. I am Anil Topal, and today I will be presenting the paper AID monitoring system. Sorry for the introduction. So I'm Anil Topal, and today I will be presenting AI-driven monitoring system for detecting people using mobile phones in restricted zones. And my co-authors are Ankana Datta and Aruna Dasgupta, and we are delighted to have work under the guidance of Professor Mumakar, ma'am, and she is also one of the co-authors. So let us proceed. Now for the introduction of the problem, like in today's generation, using a mobile phone is a very common practice for everyone, but in some places, especially in the villages, the introduction of jammer systems, which prevents us from having any phone calls or such that, but to prevent accidents. But not all places have those kind of facilities, like in the gas stations, in the hospitals, or in any type of pedestrian crossings. And accidents may happen due to the use of mobile phones in those places, and to enhance safety of the public and to reduce this kind of accident in the future work, we have labeled those zones as our restricted zones, and we have made a model to detect those individual persons live real time there and notify them by SMS so that they can stop using their phones and for the safety purposes. So the key challenges we face in our model making, first of all, was data collection. Now, CCTV data sets are like very much available in any other data set, like in Kaggle or Lobofo. But the data set which align perfectly with our required ones, like people talking over phone in those restricted zones are like very much rare. We hardly could like get 100 or 200 of those, and we have to like work on those only. And since these type of data are like government protected, so getting data set directly from governments was not allowed for us. Second was the mass monitoring, like getting counts of people in the video data sets are like very much rare. Like we have seen like detection of people not using helmets and so, but those are like mainly focuses on the roadside area and have a very less number of people considered to dash of the busy streets of Kolkata junctions. Third, we have to distinguish users like even after we have distinguished the peoples, it's not easy like we have to identify whether the person is not holding a phone, holding or using a phone for a call. And last, detection limitations like the camera resolutions, the angle, the exposure, and the amount of the person visible directly to our camera CCTV lenses. So moving on to literature inputs, where we have did some research. The main area focuses here are using deep learning modules for real-time detection of phones, and one of state-of-art object detection tracking system for identifying drivers using phones, which is a normal case. And we have got a prototype only, please mark, prototype only for using of unauthorized phone use in restricted zones only, and not a physical practical case has been developed for this one. Next, here's a methodology on which we have worked on. So first, the live data set is being captured from the CCTV cameras and the segmented into frames at a rate of 10 FPS, which is 10 per second. Then we have resized those into 640 pixel frame for the pre-processing. Then we have used yellow V8X. Now in this context, like in for yellow, we have like many versions like 5, 6, 8, 11, or even in one we have the ML, XY, different versions of nano, extra large, but we have used yellow 8X because it can be like further, the model can be quantumized to a very low level and can give us the output in like 0.02 seconds real time only. For that reason, we have used yellow 8X. That model is used to detect the phone and the person in the frame. In the stage 4 includes annotation of those frames using our dual bounding boxes system for the phones and the person and mark those boxes. Then we have calculated distance between the person and the phones for identify whether they're using the phone or not. For this, there is an interesting algorithm behind them, which I will explain in the further procedure. Then, if the person is detected using phone, then that is saved with the timestamp in our database, and that will be sent to the model to evaluate, and then it will send to the person's phone. As of now, this part is like normally in real-time scenarios, government uses the Aadhaar card identification parts for that purpose, but since it's like restricted thing for common people like us to work on, so we currently don't have that access of Aadhaar card information of the people. Then here's the distance calculation scenario, and this one is particularly for the multiple case scenario. So this one is especially for the multiple scenarios, like if the frame has a like thousands of people and have lots more, and there's a multiple use. So first, here is one example of having a yes, and that's one having a no. So first, if our model detects a person, then we have taken the center of the box. From the center, we have taken the inverse diagonal of this half diagonal part of this thing, and the smaller one is the detected boundary box of the phone. Now, for the person who have detected the whole face and a parts of his upper body, and the phone is detected here, which is the phone full part. Now, if the person, like this is the person zero and this is the center, then we have to take in this area for accountants. And if a phone is detected something like in this area, then it is detected as non-talking, like in multiple case scenario. For imagine like having 2-3 people having different type of people boxes here, and for each of them, suppose they all are holding a phone, so there will be like multiple boxes, and they are like intersecting over each other. And to detect the phone of that individual person, we are using these area sets. Now, if a person detected in the face will be in this area, and the person ear will be like in this area or in this. For that case, if the phone box is like we get intersected over this triangular area, inverted right angle triangle, then that person is talking over the phone. Now you may consider that there are left-handed people also. For those here are we consider, but in India, like almost all the population of Indians are like right-handed, and they will for the first time basis they will use that right side of their body part to hold the phone, and basis on that our model will first detect on the right hand side angle whether the phone is there or not. If not, then they will go for the left hand side, but the priority one is on the right hand side, and that's the case in this case. And in case of and yeah, then this is our model work for. So first, like I have told, like 60 camera, then the live footages will be converted into frames, and then the images will change to the V8 model. Bounding box predicted, then we will calculate the coordinates, which is like the algorithm for taking the centers and calculating in right inverted triangle distance calculation, then compare the thresholds, like whether it's within this area bounded or not. Then if positive, then we store the people snapshot, like to be remember only this people boundary box area, not the whole picture thing, so that we can only identify that particular person. Then we will generate text over the images as of now, because we don't have the Aadhaar link in our case, and that's the end of our model. So here's a result. So as previously we have seen in our literature, we have done a research on using deep learning models, and Also, one using state-of-art object detection on a phone. So we have used one of those models for our single boundary box detection system, which detects the person talking with phone. As you can see here, the person talking with the phone. This is our initial model. But these can only be done in places of like libraries or in gas station where hardly any crowd gathering occurs. But in case of pedestrian crossing or like in the last time hours, a large number of people gather. So in that cases, using these type of boxes can overlap with other phones. Like in this, and the model could detect this phone area of this phone of the other person instead of this phone. And to avoid this type of unwanted situations, we have used our dual box bounding system. Although the accuracy is less than reasonable, but it gives us a better visual. Like this one, the single one, and it's displaying that people is talking on the phone, and here's the distance. Okay, so this one is kind of another one. So single test like here. First, the person box is detected and the phone test. Please note that this type of this algorithm works only when a single person or two or only one cell phone is detected. Like only one phone box is detected here. In that case, this will work. Like the center of the phone and the boundary box will be calculated, and their central distance will be calculated here in Euclidean distance formula, like here's a right angle triangle to this calculated distance. And if that distance is like half of the diagonal of this bounding, or like this half diagonal, if that value and this value are within those or equal, in that case only the person will be talking over the phone, and that's where our DBS model works. Okay, so for the future scope, as we are currently working on the data set, we are thinking of like adding of multimodal integration of using audios and video into a phone detection set. Now, you may ask the question like, why using cell phone? Like, because nowadays Bluetooth connections and headphones are like more convenience for us. Like, you can all easily talk over the headphones like connecting Bluetooth. So in that case, normally we don't use cell phones. In that cases, we are like updating with the audios and videos so that we can use like read the lips of the person detected movements, like lip movement in case of using earphones, and using the audios so that we can detect whether that person is talking or not. Second, we have the real-time deployment system, like for the thing which I've done here are like the data set which have been taken are for 1800 pixel frames, but in India we don't have CCTV cameras of having 1K pixels for all the cases. Like commonly in the congested roadside areas, they don't have such high quality camera pixels, and the qualities are too much hazy. And those are pixelated, which can cause one short pixel errors also. And to avoid that, better needs like more richer data set for that. For the low light resolution cameras, then concluding for our paper, we have this robust system for yellow ATS model for detecting phones, and we are like currently brainstorming and working on the advancement system, and we will hope to get a better system for this. And these are some of the references which we have used for our studies, and that's all from my side. Thank you, and I'm open to any question from your side.
We just thank the speaker briefly, and then we can take certain questions. Maybe can we have the speaker to remember first? So, sir,
Yes.
so you had taken this half of the diagonal, and if it was within that distance, you have taken it to be using that photo. How did you come across that particular figure? That's number one. And number two, I might have missed it, but how are you plotting the coordinates of that box? Like, what are you using to calculate it?
Okay, so if I'm getting correct, then first of all, your second question consider how we are getting the coordinate systems of the boxes. So let me clear you first. In our yellow ATEX model, which is you only look once, they have the architecture between in have like tuple type JSON format, which consists of the x1, x2, y1, y2 coordinates, and it can be modified into xy.
The speaker is not working. So we could kindly fix it. Still not working, I guess. Sorry for the inconvenience. Just a moment.
Hello.
This one.
Cordless mic computer.
Okay, so for your second question, yellow give us x1, y1 and x2, y2. So let me get here. This one is an axis like x1, y1. It's a coordinate system or 2D, and this one is x2, y2. From here, we get the coordinate system of this one, which is x1 and y2, and this one is x2 and y1. From this, we are getting the coordinate system of all the 4 A corners, and from here, we can get the center. Like this is a calculation of the right angle triangle. From here, we're getting the center, and this is the like median area. So doing a calculation based on this is like easier for us. So from here, we like doing a simple calculations of right angle triangles only and getting the coordinate system and all the area. And for the first question, could you repeat once for that part?
Why half the time?
Okay, so as I have told that we are taking like, yeah, like you can see the picture in here, like the people bounding box here. Here the centered part is like more of the percent nose, and our model normally detects the centered of the model centered of the box based on the percent nose or the area which is linear to that side of the person, and we are taking till this area. So if we consider the face of the person, no matter how much big or small it is, the total face would get covered only in like this area or more than that. And if we consider about the biology of human ear, they will be located like more or less like in this area, like this, because those are the proportions we are given to go on with, and based on those, the the ears can be like here. It could be like it can be here also, like the ear upper portion and the lower portion. But if the mobile phone is detected and if the box is located here also, then if we consider this box, then that some portion of that bounded box can also be plotted within this triangle. And this way our model also get results. As I have told that if the mobile bounded box falls under this area, then it will be detected. And that's what
One more question.
My question, my question got answered. Okay. So anyone else? One more question from my side. So you have you have provided with the number of training images and the validation images I can see, but what's the size of the test images? Because you show an accuracy of 85% almost. So what's the
our testing and validation images are like similar way, and those are the same numbers of 140 and 137 only. As in the beginning, I have told that those are government secured photos. So getting a bunch of those was a great deal of us.
that is fine, but you could have kept a separate set of images which could have been used as test data set. So do you mean that these are on the validation images? So this accuracy that you got are on validation images?
Those accuracy are on the test data set, and our ratio of division data split ratio was 7:2:1 in this.
Okay.
7:1:1. 8 and
Anyway,
1:1.
okay, all right. Anyone else? Right. Huh?
Okay.
One more question?
Yeah. So I was trying to understand a bit more about something you were talking about, the right-handed. You were considering that Indians are mostly right-handed. Could you walk me a bit through that assumption that you had?
Maybe a little faster, right? Yeah.
Okay, so like we have seen some papers, and almost like 90% or like 80%, you can search on the Google's only, like most people are like right-handed, and in times of normal like habit, you can say naturally, most of people like pick the phone in this way or like this way talking in this way in the first reference. In those cases, we are consider that lower triangle area for those. And if phone is not detected in that area, then it will automatically get shifted towards the opposite lower right angle triangle.
Okay, that
That's
answers
the
my
first
question.
preference and then second.
Okay, that answers my question. Thank you.
All right, so let's thank you once again. Thank you. All right, so let's move on to the next work. So the next work is overlapping community detection using dynamic residual deep GCN. This is going to presented online by Muhammad Nurul Muttaqin. Is he there online? Is Nurul there online? Okay.
Yeah, can you hear me?
Let's start the presentation.
Hello. Okay, can you see my presentation?
Yes, it's visible.
Okay. May I proceed to?
Audible as well. Yeah, please go ahead. Thanks.
Oh, thank you. Okay, so good afternoon, everybody. I'm here, Muhammad Muttaqin. I'm from Bangladesh University of Engineering and Technology, and this is a joint work with Professor Dr. Saidur Rahman from Bangladesh University of Engineering and Technology and Dr. Iqbal Hussain from University of Arizona. So our paper is overlapping community detection using dynamic residual deep GCN. So this is the overview of my presentation. Let me start with a small social network. So please look at this network. Can you identify the communities in this network by just looking at this? Surely no, because human eyes struggles with structured, especially graph structured data. And in fact, if we identify the communities in this graph, we'll find two communities. So community detection actually important for various reasons. For different organizations, either government or non-government, they can observe the community of interest, controlling public sentiment, and many more. Moreover, overlapping communities are more important because there are some nodes who shares in both communities. So for example, in social communities, we can say these are critical person, and they are also important for different reasons. And here we can see some importance from the perspective of social network. However, what is the community? For a given graph, we define community as a dense subgraph of the graph. I mean dense means in the subgraph, the connectivity between the edges is higher, and if the connectivity from these nodes from the outside nodes, then the connectivity is lower. So here you can see we have a sample graph, and in this graph, we have two sub-communities, and the connectivity among these communities among the nodes in this community is higher, and outside nodes is almost no or lower. Now, let me say another parameter, which is we say as community diameter. So community diameter actually like graph diameter. So for a graph, we define diameter as the maximum shortest path distance between any pair of nodes in the graph. Now, here we can see we have two communities. For example, on the community on the right side, the community diameter is 4. That means in this community, the maximum shortest path distance is 4. On the left side, we have another community, and the community diameter is 3. That means from any pair of nodes in this community, the maximum shortest path distance is 3. But why this is important, we'll clarify this later. Now, let me go on our problem. The problem we are going to solve is that we'll be given a graph and as well as its node feature matrix X. So we can represent a graph as a CC matrix, which is A, and the node feature matrix, which is X. So given this, I mean, as a CC matrix and node feature matrix, we'd like to find the communities of this graph. And we can represent the overlapping communities by a community affiliation matrix. So what's a community affiliation matrix? Here on the right side, you can see a matrix. In this matrix, rows represents nodes. So nodes of this graph, for example, this row A, I mean the first row represent node A, and the second row represent the node B, and so on. And the columns represents the communities. So here we have two communities, that's two columns. Now, for example, for node D, here we have the entries is 1. This value 1 means this node D belong to community C1. And also here also C1. I mean for C2, this value is 1. That means this node also belong to community C2. That means this node D is an overlapping. However, node C is not overlapping node because here we have 1, 0, and you can see visually from this graph and this is a matrix representation of community. So we have given the graph, we would like to find the community affiliation matrix. So we'd like to see some related and relevant literature. There are a lot of works on community detection. There are some algorithmic approaches. Here you can see by many authors, and then some works, they try to consider some kind of machine learning approaches. So there are some kind of semi-supervised approaches. There are some unsupervised approaches, some kind of negative matrix factorization based approaches. So there are some classical approaches. However, considering to these classical approaches, GCN-based approaches, especially graph convolutional network-based approaches performs better. For example, this is a good algorithm by Xi et al., which is known as SLPA. Here we visualize the largest community detected by two algorithms. One is a CNN-based algorithm and another is a classical method. And you can see the largest community detected by this Shar and Gunman's algorithm is better because it uses graph convolutional network, but the largest community detected by Xi et al. Is not that good. You can see some nodes which is not connected to any other nodes also considered in the community. So it doesn't make sense. Still, this method has some limitation. So the main limitation is that the method used in NOCD by Shar and Gunman, they considered a GCN which is shallow. That means it considers only 2 layers of a GCN. And as it considers only 2 layers, that means it can aggregate information up to 2 hops. That means if you have a community which have diameter like, for example, 3 or 4, then this GCN method will suffer. It cannot detect that community better. So that's why our goal is to detect communities with larger diameter. And one, intuitive solution, just go for deep GCN. And if you go for deep GCNs, most of the deep GCNs, they are designed for point clouds or this type of regular graphs. If you consider a point cloud, here every node, you have same number of nodes. And if you have same number of nodes, then it cannot be generalized for general graphs where every node, you have different number of neighbors. In point cloud, we consider for every node, we have 4 neighbors or 5 neighbors. This is in our hand. But in general graph, for every node, you have different number of neighbors. So like, taking these deep GCNs or applying this deep GCN in a general graph will be a bit problematic. So now our goal is to resolve the issues in shallow GCNs in existing NOCD model. So we'd like to propose a deep GCN that can be applied on a graph where every node can have different number of neighbors and if neighborhood size can vary. And therefore, as we want to go for deep GCN, if you want to go for deeper model, you need residual connection. So we incorporate the idea of residual connection, and you also need some kind of dilation and dynamicity of edges, which is helpful to remove over smoothing issues and like gradient, exploding gradient or vanishing gradient problems, solving these issues. So we'd like to develop a method where we can apply any graph with larger diameter and we can detect communities better than earlier methods. So here is here you can see the conceptual comparison of our proposed method, Dynared GCN with Bernoulli-Poisson decoder. So Dynared GCN actually the encoder, Bernoulli-Poisson model is actually the decoder, and here we incorporate most of the important ideas and we get a better model. We see in the result section. Now here you can see the overlapping community detection model. So this is actually our model, which is actually similar to earlier NCD works, but our improvement, our main focus is this encoder part. So here in this encoder part, we'd like to encode communities with larger diameters, and therefore we'd like to get information for a node from larger than 2 hops or more than any hops. So that we can capture larger communities. So you can see this is the input graph. Then we have the encoder. So this deep GCN encoder will generate the community affiliation matrix. Now, once you have the community affiliation matrix, we can use the Bernoulli-Poisson based decoder, which actually try to reconstruct the original graph from the given community affiliation matrix. And from this reconstruction loss, we would like to train the deep GNN encoder. And it will give a feedback, right? So it's an unsupervised learning feedback. And from this unsupervised learning feedback loop, we'll get better and better community affiliation matrix. Now let's focus on our proposed Dynared GCN encoder. Here you can see it's a deep GCN encoder, but we say Dyna because in each layer we consider different neighborhood. Actually, from the original neighborhood, we augment the graph. And from this augmented graph, we also do some kind of subsampling to ensure dynamicity, which is important to reduce the over smoothness. I mean, it incorporates a some kind of variance which actually reduces over smoothing issues. So this is our deep-JSON block. This is one block, this is another block, and this is our residual connection. So in these models, this is our architecture. This is the architecture of our encoder. So given this input graph and the feature matrix for every node, I mean, for every node we have features. So we'll get the community affiliation matrix. So if we go for details of this architecture, you'll see here we can actually incorporate the idea of residual connection. So this ReLU part actually the original shallow GCN, but we incorporate this residual part, and then it helps for exploring on vanishing gradient problem. Then we also get the idea of dilated aggregation in our model, which is actually used in earlier deep GCN model. But we need to incorporate the idea of dynamicity of edges, and here we have two steps. And the first, to incorporate the idea of dynamicity of edges, for a given graph, we actually augment the graph up to second hop. So we have an augmentation algorithm, and from that augmented graph, we actually subsample the neighborhood, like 50% neighbors. So once from this augmented neighborhood, we subsample a new neighborhood, and this subsampling actually happens differently in different layers. So considering all of this, this is our DynaRes JSON encoder. So here, this is our graph augmentation algorithm. I mean, you can look at this in detail in our paper. So actually, this is our main overlapping communication algorithm. So this actually, this idea we actually explained in earlier in our full model. So this is the full algorithm. And here you can see this is our Bernoulli-Poisson loss function. So this loss function actually comes from the idea of Bernoulli-Poisson model. If I say the idea intuitively, the more community do not share, the probability of getting edges among these two nodes is higher. So this is the key idea. So if two nodes have more communities sharing, like if two nodes share one community, then the probability is lower. But if two nodes share three communities, then the probability of having edges among them is much higher. So this is the key idea of this equation that I explained intuitively. So these are our data sets. We actually use two kinds of data sets. This Facebook data sets actually considers human labeled data. I mean, the communities are labeled by humans, and we have large data set to test the scalability of our methods. So it uses computer science, engineering, and medicine. So this actually very large data set. So we use intuitive groups as communities. So it's not human labeled. So these are evaluation metrics. We actually consider normalized mutual information, which is actually an information similarity metric, and it is actually better than similar other metrics. So use this. Now this is our result. So here you can see in this part, we consider the graphs without no node attributes. So in our model, we just give identity feature as node attributes. So you see, we compared with Big Clam, Cisna, APM, SNetOC. So these are very good methods for community detection, and our most
3 minutes
relevant.
left.
Thank you. So we have our most relevant method is NOCD. So we compared with also NOCD, and we get significantly better. We also do significant tests based on statistical significance. I mean, with 95% confidence score. So we take 50 different initialization. For each result, we take this value actually mean over 50 different initialization, and then we do the statistical significant test. So you see, a significantly better our method. And then if we incorporate the S features, in this case also our method either better or comparative. It actually, in one case, our method is lower, but in all other cases, it performs either better or comparatively significantly better. So here, this is a visualization. So actually, this is a small Facebook graph. So we apply our method and some other method to visualize the largest cluster. And you see GCN-based method performs better, and our DynaRes GCN method actually better than also NOCD method, because here is some part in NOCD that should be in the largest cluster, but it is not detected by NOCD, but our method can do. And some other classical method actually cannot do that good. You can just look at visually. So this is one thing which I want to highlight, that because I said our method actually aware of community diameter, and you can see as we consider deeper models, so model depth actually correlated with community diameter. So if community diameter is higher, then model depth is higher. If the community diameter is lower, then intuitively the community model depth should be lower, and it happens from our experiments. So this is our execution time. So from our execution time, you can see our method also very scalable. I mean, it's very good in terms of our scalability too. Like 808 seconds, it actually in terms of seconds, and it's not that much minutes. So in conclusion, I'd like to say that method is
1 minute left.
significantly better and or comparatively better than many other methods for overlapping community detection. We also attempted to resolve some issues in deep descent training in terms of irregular graphs, and future works should consider weighted graphs and edge features for overlapping community detection tasks. Actually, we have some work ongoing on this. These are some references. I'd like to thank for our grant from BUET, and I would like also thank Codecrafters International for their support, which actually helped us to participate in this conference. Thank you so much. If you have any questions.
All right, so let's first start by thanking the speaker briefly, and then let us have some questions. If you have any question from the audience, please. So, Arindam Chatterjee, is a question, please.
Yeah. Dear speaker, I really appreciate the effort you have given. One question, if you go back to page number 21, that's how you're actually constructing the augmented graph. Can you, I know it's a really detailed procedure, but can you just briefly explain?
Yeah, I can.
Sorry,
Sure.
page 19, it should be earlier.
Okay, I'm explaining. Thank you for the question.
How are you actually,
So,
are you ensuring that augmenting that graph is giving you access to communities which are larger than the diameter?
no. Actually, augmentation. Yeah, I'm explaining. Thank you for the question. Actually, this graph augmentation, it ensures to make a model deep GCN which can go deeper. I mean, like our model can capture larger community diameter because we can employ as many as layers we want. In the earlier method, it has only 2 layers and it is limited. Like you cannot change the layers. If you just change the number of layers to, like, for example, 5 layers or 4 layers in this shallow GCN model, earlier model, it will perform much worse. So now, using this idea of graph augmentation, and then we also, let me go this figure. Actually, this figure will help you. So here, I mean, in every layer, we change the graph in some way that actually introduces some kind of variance, and this variance helps us to reduce the problem of over smoothing. Over smoothing means if you just go on like number of players, if you just increase the number of players in a shallow GCN without considering this dynamicity of edges, the performance get worse because after some layers, like 4 or 5 layers, all the nodes gets the same feature. I mean, you lose the variability. So that's why, like for every layer, we augment the graph. For example, in D, this is our augmented graph, but in E, we sample a new graph, like we sample the 50% of nodes from this augmented graph. And in another layer, we also do this sampling again. So we get another augmented graph, but this graph a bit different from the earlier layer. So like to capture the larger communities, like which has much larger diameter, we actually can go for any number of layers in this GCN model, which actually we have shown in this figure. Like here you can see the max MCD means maximum community diameter, and this is actually model depth. I mean, red is the model depth. Now you can see if the community diameter is larger, like for example 5, in that case we need deeper model, like 7 layers of I mean in the depth. But when we have, you can see that, like for example diameter is low, for example 2, then a model with like 2 depth is fine. But you know, it's the empirical work, so it will not get always exact, but you can see the pattern, right? For example, when community diameter is low, it should be lower. When community diameter is higher, model depth should be higher. So this is the way we capture larger communities. Is this clear, sir, your question?
Okay, thanks, I guess. So we will take another question, please.
Yeah, my question was not answered. I mean, my question was, you were saying that
your GCN method doesn't work well for detection of communities with larger diameter, right? That was the statement, right?
Yeah.
Yeah, but I think what all that is needed is you have to use more computation using a model with more deep layers. That's what you are talking about, right?
Sir, can you please repeat?
So what he's trying to say is, say you have used a very robust architecture, very large architecture. So the number of computation that you are doing eventually through that architecture is quite large, right? So what would be the number of parameters in terms of millions or billions that you use for this architecture? Could you have you
I mean, what's the number of parameters?
Yeah, number of parameters in millions. It should be in millions, right? Because you are using residual.
Yeah. Okay, yeah. That's a good point. That's really good point, because if you use a model with only 2 layers, then in that case, number of parameters is like, if you, for example, let me give the comparison. If you use a model with only 2 layers, and if you a model with 4 layers, then your number of parameters will be just double, right? And if you consider a model with 7
Question
layers,
here is
then
what's the number here? How many millions? Tens of millions, 100 billion.
Okay, actually, I didn't
You have not
measure that.
calculated that yet.
Yeah. I ran in I mean RTX 32 GB GPU and it worked,
Which
but I
one?
didn't.
Is that?
Yeah.
Once again, can you please repeat?
Yeah.
Which one?
Yes, I ran in 32 GB RTX GPU machines,
RTX.
and I also
RTX 3000 or 4000s?
32 GB RTX GPU machine. I mean, GPU memory was 32 GB, and also because it also depends on the graph size, input graph size.
Yeah, the input graphs were small actually.
Yeah. Sometimes it was smaller. Let me say I have 2 sets of data sets. So I have 2 sets of data sets. For example, here, like for Facebook data sets, these are small graphs. Like you have
sorry
at most.
to interrupt. We have exceeded our time. We will move on to the next presentation. All right, thank you.
Okay,
thanks.
Okay. Thank you, sir.
So for the next presentation, I call upon Surya E. And the name of the paper would be Deep UIR Net Underwater Image Restoration Using Residual Unit with Optimized Efficient Channel Attention Network Integration. So Surya E from Amrita Vishwa Vidyapeetham.
Hello, can everyone hear me?
Yes. Please start with the presentation.
Yes, sir. Just
share the presentation.
Yes, sir. Just little technical issues. Yes, sir. So is my screen visible?
No, it's not visible yet. The admin guy, kindly check what's going on.
Yes, sir. Just checking.
Yeah. So the thing is that if you can't start in next 1 minute, maybe we can start with video that you have sent us.
Yes,
Is
sir.
that
Yes, sir.
right with you?
Yes, sir. Just a minute. Yes, sir. Is it visible now?
Not yet. So we are going to start with the pre-recorded video then.
All right, sir. Sure, sir.
Auditor, could you kindly check if the pre-recorded video could be started now? Because we're short of time. You can stay online so that the audience can ask several questions.
Yes, sir. Definitely, sir.
Thanks.
Residual network. Hello all. My name is Sam Raymond, author of the paper titled DPO Underwater Image Restoration Using Residual Network Optimal Efficient Channel Attention Network Integration. The contents of the presentation will be introduction, existing systems, dataset description, the proposed system, results, and concluding with the completion points and future. What is underwater restoration and what are the consequences it suffers from several environmental factors such as attenuation of light, color distortion, and contrast issues. So whenever we click photos of images in underwater, these factors make it difficult to use them for research and also detect certain small objects in them. So we propose a deep learning-based method to enhance the quality of such images, making it suitable for practical applications. So certain new techniques using CNNs have already been proposed and have also shown very good results in restoring underwater images. So our project proposes a novel approach, which is also computationally efficient by making use of resilient architecture, integrating efficient channel attention module. So the existing systems such as AquaGAN, MSP, GM, and several other CNNs and GN models have already been proposed, but they use a lot of post-processing of the obtained results to enhance the quality. So we tend to avoid this post-processing of images. And seeing based methods also are effectively done. But all these again have used a lot of post-processing of the obtained results. And one more point is that channel attention models, which we focused in our work, hasn't been explored much with respect to these deep learning techniques. So coming to the dataset description. The dataset we used for the work is LSUI, which is large scale underwater images. So we used 2000 images, each from degraded and the corresponding ground truth for training purposes because of computational reasons. So as you can see on the left is the LSUI dataset sample, the features which consist of the degraded image and the corresponding ground truth image. And on the right, you can see the data set split, which we use for training, which is 80% training, 10% testing, and 10% validation. So the proposed system is, as I mentioned before, it is incorporating the efficient channel attention module to the residual unit. So this unit on the residual unit is a combination of two blocks, mainly unit and then the residual block. So the main advantage of this architecture is the feature extraction is better. And it also uses shortcut connections which helps in passing the input directly to output of the residual block. And in this process, it can also avoid the vanishing rating problem. And then the output of this residual block acts as the input to the decoded block. So as I mentioned, the ECNet module or the efficient channel detection module, this was incorporated into this particular residual unit and it was trained for 30 epochs. So the main advantage of the ECNet is it improves feature representation by effectively focusing on important channels and reducing the or ignoring the less significant ones. The data is processed using a 1D convolution layer as shown in figure 3. And this is used to calculate the attention rates for each of the channel and then enabling the network to effectively understand the channel dependencies or the relation between each of the channel, the feature maps. So the further work is that we tried with different activation functions in the ECNet, which is the rainbow, seal, and the hard stop. And upon experimentation, we found that hard space function had better results compared to other two activation functions. So this is the proposed system architecture, which is shown in figure 4. So now coming to the results. So we validated using MSC loss and SSIM and also PSNR. So the last column, which is the hard switch in the ECA, that is the proposed system of hard work, that is the DPRnet. So the SSIM of 0.998 and PSNR of 74.851 dB per decibels is remarkable. And to show the effectiveness of our work, we also compared the proposed DPRnet with several other models, be the UNet family or the GAN family, I mean the GANs, the cycle GAN. So upon the experimentation and the comparison, the last row, which is the proposed model of our work, it indicates the SSIM of 0.998 and PSNR 74.851 decibels, and the loss, which is 0.003 dB. These values are relatively better compared to all other models that we have experimented. And figure 5, which is on the right, shows the loss plot of the DPRnet. So as we can observe here, the training loss and the validation loss are gradually decreasing for the 30 epochs that we train, and are also not overfitted or underfitted the data. So on the left again, the top one is the input images that we gave for training the model. And the one on the bottom left is the proposed results of our work, which is using the DPRnet. As you can see, the quality of the images is certainly enhanced, making it clear the objects or the plants or the mere aquatic animals in the images. And it's also facilitating the research and also for practical applications. The images on the right side, on the first one, it's basically the results of the UNet model. These are just shown here to show the effectiveness of the work, and it's a comparison. And the one in the right middle is the results of the DPRnet with radio activation function. In the one below is the DPRnet with seal activation function. So compared to all these images, figure 7, which is the proposed result, this is better in terms of the quality and the contrasting and saturation of the images. So to conclude with, the models were generalizing well for the ECNet data that we train. And as discussed, the rescue that with ECA using Hartley's function, that is your DPRF model, gave better results in terms of image quality compared to their base models. And the future work for this can be extended to underwater video restoration as well, wherein you analyze each frame and then train the models based on each frame you obtain. These are some of the references that we use for completing this project. Thank you.
Let us thank the speaker briefly, and then we'll have a few questions if you're interested. Yeah. Let us connect, please, quickly.
Am I heard?
Who wants to ask a question? Can you kindly raise your hand? Who wants to ask a question? Mute or mute. No, no one? Busy. No one? Surya online?
Yes, sir, I'm here. I am speaking on behalf of Revant.
We just went through the video of the presentation. Okay, so no one from audience, I guess. I would like to ask a few questions. So the first question that I would like to ask is, no ablution study was seen in the so in the video. I have not seen any ablution study. Have you guys done any ablution study?
Sir, this was majorly based upon a student project for the campus itself. So we haven't done an ambulation study at that time, but we are going to do from now on, sir, as a continuation in this semester.
I see, I see. So, and furthermore, I mean, the architecture seemed very large. Lots of blocks. What kind
Yes,
of
sir.
computational resources did you use, and for what's the number of hours for which the programs ran?
Yes, sir. So we ran it on two base systems, you could say. First one was a normal HP Pavilion laptop, which used GTX 1060. The second was the Kaggle notebook, where we used T4 GPUs. So when it ran on our system laptops, it ran for approximately 2 hours, and upon which it was completed. And in our Kaggle notebook, where it used the T4 GPUs, it took around 1.5 hours to 1 hour.
So, did you use like quantized versions, or what kind of versions do you use? Because I mean, look quite robust. I mean, the architecture looked quite robust to me. So I thought maybe you would have used GPUs, large GPUs. I mean,
No, sir. The entire, you could say the entire aim of our project is to minimize the load and make it more efficient on systems itself, because this is supposed to go on further to the further studies could be to use the same technology for video analysis rather than image analysis, because our aim is to help underwater divers itself for underwater operations such as internet cable fixing and repairs. So during those stages, videos are more required rather than just images being cleared out. So our main focus was to reduce the load.
but to train and to deploy, these two are not the same, right? You can train on very large data, and then you take the matrix and you deploy it in a smaller quantized manner, right? So you can do that. That also can be done. So
Yes, sir.
anyway,
Okay.
let us thank the speaker once again. Let us thank Surya. All right. So we are going to move on to the next presentation, which is from the same university, I guess, Amrita Vishwavidyapitham. Tanya Simhadri is going to present the paper, Deepfake Image Detection Using Lightweight Attention Integrated Mobile Net V3 Model. Is Tanya available? Tanya?
Sir, am I audible?
Yes, you are audible.
I'd like to share my screen.
Yeah, if you could kindly share your screen, please. Yes.
Yes, thank you.
Your slides are visible as well.
Yes.
You can start. Thanks, Tanya.
Yes. So our paper is Deepfake Image Detection Using Lightweight Attention Integrated Mobile Net V3 Model. Our paper ID is 029. These are our contents for today. A little introduction on the deepfake topic. The term deepfake comes from deep learning and fake content. So basically, deepfakes are manipulated or content that is created using deep learning. So these use generative neural networks and deep learning to modify or create images and videos. While it is useful for art, animation, and entertainment, deepfakes also pose ethical and security concerns. Malicious use includes fake news, manipulated material, and reputation damage. So, detecting deepfakes involves subtle visual patterns, identifying subtle visual patterns and temporal inconsistencies. So, in our paper, we are proposing a fine-tuned mobile net V3 model, which is integrated with self-attention layers, and we have compared our proposed model with 5 different popular CNN models, that is ExceptionNet, Inception, MobileNet, EfficientNet, and Inception ResNet. Yeah. So the main reason why we have included self-attention mechanism is because it effectively focuses on crucial areas, boosting the model's ability to detect manipulated artifacts in deepfakes. And our proposed model was able to perform better than the other 5 models, achieving the highest F1 score of 98.46%. And the proposed model also has minimalistic memory and time requirements, supporting real-time applicability. These are some of the papers that we have referred during our research. The first one is Efficient Nets for Deepfake Detection. This paper basically has done a comparison of efficient net versions, that is B0 to B7. The second paper, a deepfake detection system using deep learning. Here they have talked about a lack of diversity in the data sets. That is why they have implemented augmentation techniques, face cut and random arrays. The third paper uses ExceptionNet and MobileNet for deepfake detection, and the pre-processing and a voting mechanism has been implemented there. The fourth paper here, they've shown how F1 score is a reliable identifier for deepfake detection, which we have also considered during our research. And the sixth paper uses a unique person of interest, and the profile is used to identify images as real or fake. And they have achieved an accuracy of 95.75%. And these are the other papers that we have referred. Coming to our dataset, we have taken a DFDC dataset that was published by Facebook in 2019. It is Deepfake Detection Challenge, which is a benchmark dataset. And the entire dataset is very huge. We have considered a sample of the DFDC dataset. It consists of 400 videos, which we have converted into images and taken as our data. 400 videos for the training part and 400 videos in the testing as well as validation. And the video features individuals' faces, and to create the fake content, they have used deepfake techniques to generate the fake data as well. And we have shown a few samples from our dataset here where we can see there are modifications in the people's faces. Coming to our proposed methodology, we have taken the initial data that is in videos, and these videos are converted to frames. And next we have done data augmentation. Next, face detection and cropping of the face area. And then train test validation split, model building and training. and model evaluation using the test data, and then classification into real and fake. We'll be explaining each of this in detail. Coming to data pre-processing, for every video, each second is considered as a different frame and a frame is extracted. And we have also augmented the data by performing horizontal flip and right shift of the image to ensure diversity to different kinds of images. After data augmentation, our images are a total of 11,000. So after this, we have done face detection using dlib library in Python, and we have cropped it so that it's easier for the classification as fake or not. And we have done label encoding where real is considered as 1 and fake is considered as 0. For our train test validation split, we have taken 70% for the model training, 15% for the validation, and 15% for the model testing. Coming to our main methodology, we have compared the 5 CNN models, that is EfficientNet, ExceptionNet, InceptionNet, InceptionResNet, and MobileNet v3. Out of these 5 models, we have found that MobileNet v3 has given us the best results. So we have chosen this model and we have chosen to fine-tune that. For this, we have used self-attention layers. So basically, self-attention layers are integrated to capture dependencies in the image and identify the manipulations. They use queries, keys, and values. That is, queries look for the regions in the image that might indicate the manipulations. Keys are used to compare this part of the image with the rest so that we can identify the modified part. And then value is the actual value of the input that is used for the layers. Now, these based on this, by the given formula, we are calculating the self-attention values, and these are used in our deep learning layers for identifying the fake content. In our proposed architecture, we'll be showing it here. We have loaded the pre-trained MobileNet model that is pre-trained on the ImageNet dataset. We have added a few dense layers, and for the self-attention addition of the self-attention layer, we have considered 3 positions to experiment. The first one is after the first dense layer. The second position is after the second dense layer. And for the third case, we have added 2 self-attention layers, one after the first dense layer and one after the second dense layer. So we have done a comparison of all of these, and we have found that the model where the self-attention layer is added after the first dense layer has given us the best result. Yes. Coming to our hyperparameters that we have used, the number of epochs that we have used is 30. The learning rate is 0.00001. The optimizer used is Adam. And activation functions are ReLU for the layers and sigmoidal for the output layer. And the batch size used is 64. Here we can see the comparison of the different positions of the self-attention layers. And the first case, that is after the dense layer, which is our proposed model, has obtained the best results with an accuracy of 98.6% and a loss of 0.103. And we have also compared our proposed model with the other models that we have tried, and we can see that it has the best accuracy, F1 score, precision recall, and minimum loss. And we have also compared the trainable parameters and the time that is being, the memory and time requirements. We can see that the proposed model has a lower trainable parameters compared to most of the other models, as well as the time is lower. So it is also feasible for real-time application. So a summarization of our results is that our proposed model has surpassed the other models significantly, and the inclusion of the self-attention layer has given us better feature extraction, critical feature identification, and better performance. And we have also seen that adding 2 self-attention layers has reduced the efficiency surprisingly due to overfitting. Coming to a conclusion, so the fine-tuned MobileNet v3 model that we have proposed have achieved a F1 score of 98%. The self-attention mechanism effectively captures spatial dependencies, improving feature extraction and detection accuracy. And compared to other state-of-the-art CNN models like Inception v3 and ExceptionResNet, the proposed model has performed better with minimal increments in parameters and least inference time. The future work for this research will include cross-data generalization, enhancing model explainability through explainable AI, and addressing the ethical concerns for real-world deployment. Since our research is based on deepfake content, it is very important to consider the ethical concerns which we plan to do in the future. These are our references. Thank you.
Right, so let's thank the speaker. Let's get started with the questions. If you have any question for her. No one wants to ask any question? Any question from the audience? Okay, all right. Then maybe I'll ask a question. Can you go to the flowchart kindly?
Yes.
Yeah, so in flowchart, you in the third box, I guess, you show that you are cropping the face, right?
Yes, sir.
Face detection and cropping, right? So data augmentation you have explained clearly, but why do you focus on the face? I mean, so the deepfake data set that you use, they are on the basis of the face only and not the background and any other thing.
The manipulation for the deepfake is based only on the face. So I think the other parts of the image might manipulate the system sometimes. So during training, we have only used the face cropping method. But during testing, we have included the general images and the model is able to work through that as well.
And we can see that you have used fully connected layers, lots of fully connected layers. So dense layers, fully connected layers are intense, right? They are pretty intense. So the time also you have mentioned. So what's the difference between an inception? Because inception is pretty updated, right? I mean, inception is also pretty intense architecture. So what's the number of fully connected layers that are there in inception and over here? Have you brought it down a little?
Sir, actually, we have added our layers to the pre-trained mobile net model.
Mobile
Compared
net,
to
I can
inception,
understand. So
yes.
is this more scalable? What
Yes,
would
yes.
be the difference? Because
Compared to
the number of
inception,
parameters you show is quite less, much lesser than inception.
yes.
Right?
Compared to inception in general, mobile net model has lower number of parameters due to the convolution, and it is specifically designed for mobile applications. So I think mobile net itself in general is a better, like it has better time constraints and memory constraints compared to inception. So we have taken that model and we have included 3 dense layers to that, but compared to inception it is still lesser. So I think the time and memory constraints are taken care of.
What kind of computational resources have you used? What kind of GPUs have you used? Did you
So
actually run the inception models, or have you taken those results from somewhere else?
we have run all the 6 models.
Okay.
Yes.
What kind of
We have
GPU?
used Kaggle notebooks for it. We have used the GPU T4 that is there in the Kaggle notebooks.
Keyboards. Okay. All right.
Yes.
Okay. Thanks.
Thank you, sir.
Thank you, Tanya. All right. So we are in for the last technical presentation of the day, which is going to be an international presentation by Dong Nguyen. And Dong Nguyen is going to talk about Healy graph convolution neural network, deep and enhanced adaptation of interest modeling for personalized recommender system. So an interesting talk. Dong Nguyen, are you here?
Am I heard?
Yes, yes.
Okay,
You're
let me
audible.
share my slide.
Yeah, sure. Please go ahead. Thanks.
Is my slide visible?
Yes, we can see it. Thanks.
Okay, I will start right now. So, afternoon, everyone. Today I will present the Healy graph convolutional neural network. So, Healy is like a combination of like heterogeneous and lightweight model. So let's move to the outline. Wait a second. I have to adjust my slide. Okay, here is my outline: introduction, related work, methodology, experiment and result, and conclusion. So with the growth of social network and e-commerce platform, recommender system has like impact to our lives. However, traditional model based on graph neural network or GNN often struggle with handling complex and diverse data, leading to high computational cost and limited performance. So we have the two popular problem, which is like the cold start problem, when the system cannot make accurate recommendation for new user or new item due to a lack of historical interaction data. And the second one is like the long tail problem. It refers to the phenomenon where a small number of the popular item, the head, receive the majority of the interaction, while a large number of the less popular item, the tail, receive very few interaction. So this creates an imbalance in the data, making it difficult for the recommendation system to recommend items in the long tail. Therefore, the traditional GNN model face two main challenges. So first, they struggle with heterogeneous data with diverse node and edge types, making it difficult to capture the variety and in the relationship between user and items. Second, they incur the computational cost due to the need of the process complex intermediate graph, reducing the model's scalability. So to address this issue, LightGCN was introduced, focusing on the simplifying the process of aggregating information from neighboring nodes. However, LightGCN perform well only on homogeneous graph, and it cannot effectively handle complex diverse graph. So we proposed the model with the name of GCN to resolve all the challenges we have mentioned before, and by combining multi-level graph coarsening and sophisticated contextual embedding, enabling more efficient modeling of the complex user item interaction. So next to the related work, so we have discovered the graph theory. We have to discover the homogeneous graph and the heterogeneous graph, and the challenge of the multiple type of nodes and edge in the heterogeneous graph in Zhang Bang-Sen et al. In 2019. Next, we discovered we see the graph transformation. We have several methods like graph sampling. Let's go back and Falutos, 2006, graph coarsening, Dylan, Kwan, and Kulis, and 2007. And the last one is graph pruning, Shang, Huang, Jiang, and Li in 2020. Next one, we talk about graph embedding. Those are popular embedding learning like DeepWalk, GraphSage, and Node2Vec. So we will focus more into Gartney and HCN because they have the best performance when we handle the heterogeneous graph. And the last one is the graph convolution. So we adapt and inspired by LightGCN because it simplifies the GCN architecture for efficient recommendation. So to resolve the oversmoothing, we will apply the APPNP with it's the abbreviation of approximate propagation of the neuron prediction. Okay, so we next to the methodology. So this is my pipeline. It is designed to efficiently handle large scale of the heterogeneous recommendation task by combining it with like in the three main phase. The first phase is the pre-processing. We will convert the raw data, tabular data into the heterogeneous graph to handle the user and item interaction. And after that, we will cost into the smaller graph to keep the efficient interaction between user and items. After that, we will learn the embedding that represent the multiplex relationship in the coarsen graph. And we will, next to the refinement process, it will capture both the local and global interaction in the original graph. So we will learn the embedding from the coarsen graph, and then we will refine from the coarsen graph into the original graph. And after that, we will have, when we have the old embedding of the user and items, we start to using the line GCN here to prediction, make a prediction and have output with a recommendation. So this is a process of transform from the tabular data into the heterogeneous data. So the only condition is that we will only accept user item interaction and vice versa. There is no interaction between user and user or item and item. So it's like a bipartite graph. That's the only condition when we preprocess the data. Next one, this is the condition when we calculate the similarity between two type of with two nodes in the same type. So this is very checkbox. So it is like to measure the similarity between nodes. So but the problem is if you try to do this in all the whole graph, the computational cost is really high. So I have to have to think and choose the other choice. It's locality sensitive hashing, LSH. So the problem is it will efficiently group nodes with the employed to efficiently group nodes with the high checker similarity. It's like when we compare two nodes, U and V, if they have the probability to fall in the same bucket, it will proportional to the Jagat similarity score. So the higher the LSH, the higher the Jagat. So it is the coarsening process. It will iterate until the graph is no longer to be coarse. And of course, we have to set the threshold. So to avoid the critical information loss. So the delta is a at the edge is it's like the degree of the whole node. And lambda is the vertex connectivity, and k is edge connectivity. So it must be greater or equal to a total of node divided by 2. So it is inspired by the Menger theorem, and was mentioned in the graph theory. So next one, when we start to embedding the Gaussian graph, so we will using the Gartner architecture. So we started to think of like the three. The first one is the base embedding. The second one is node attribute, and the last one is edge embedding. So we will try to capture the diverse relationship within the Gaussian graph. So we will move on to the random walks for each type. So we will using meta path based random walk to generate node sequence following the relationship. And we using the skip-gram model to predict the context node from a target one. When we have a type of training sample, we will training, and the objective function is like become to the binary cross entropy. We will try to maximize the similarity of the positive pair. It's like positive is like the existed interaction between user and items. And we try to minimize the similarity for negative pairs, the non-existent between user and items. So when we have the embedding of the Gaussian graph, we will try to refine from the supernode, where supernode is the combination of many nodes from the same type, like the supernode user or supernode items. So we try to learn the local and global information from those supernodes so we can convert into the original graph. So we're using HGCN. It's like heterogeneous convolutional network. This is a projection from the Gaussian graph into the original graph. And after that, we will refine by aggregating information from the heterogeneous neighbor. As you can see in the equation, the phi is like the coefficient of the attention coefficient, and z is like a hidden representation of the node. So we keep to iterative in until we got the original graph, like a G0 from GM. When we have all the embedding from the GO, we continue to minimize the discrepancy between predicted and ground truth embeddings. So now we have a collection of embeddings of all the user and items. So we started to using the live GCN or live graph convolutional to from multiple layer to capture
3 minutes left.
Yes, user item and direction to generating recommendation score matrices. This is very popular. Although this kind of layer contribution will cause to the oversmoothing problem, as I mentioned before. So to resolve that, we will like using the APPNP. It's like the integrate teleportation coefficient like beta, like this equation, into the graph convolution process. So this coefficient will allow the model to retain a portion of the node initial feature at each layer. So it still preserve the node's initial feature and still allowing deep architecture to avoid the oversmoothing problem. So we're using the Bayesian personalized recommendation to rank the item with the higher item have interacted with the item they haven't interacted yet. So with the experiment, we will using the paper they have been already done the experiment. So we just like follow all the hyperparameter, so we can have the like the evaluate like the so we can like actually see the difference between those models. This is like training loss, accuracy, and matrix recall and NDCG.
1
So
minute
we can
left.
see, yes. So we can see my model is perform a little better, and we will not cause the oversmoothing problem anymore. If the performance comparison, so the higher layer, the higher my model is better. So it will perform the best. This one, ablation study, we will see that the embedding will impact the most. And the effectiveness study, the litigation, however, my model can handle the scalability and the accuracy. So the conclusion, so my model have to address the scalability and the computational challenge of the traditional GNN. So we hope in the future we can explore more the dynamic graph structure and consider incorporating additional site information for improved personalization. Thank you for listening to my presentation.
Excellent presentation. So anyone who wants to ask a question? So you have shown that you need a little bit of extra time more than light GCN, right? So is it coming from the coarsening part? I mean, do you add coarsening to that time, or do you calculate coarsening time separately?
Like my contribution?
Yeah.
It's like
slide where you show the times. No, the times you have shown. How many
It's
seconds?
coarsening is
How
like
many
here.
seconds? No, I'm talking about the results part where you show the time taken in number of seconds, right?
Oh yes. Yeah.
So
Yeah.
yeah, so your training time is a little more than light GCN, right? So is that because the coarsening is included? Do you really keep the coarsening time inside this training time, or do you take coarsening time separately?
Separately. It's only the training process. Yeah.
So it's actually coarsening plus this training time, right? Because coarsening needed time.
Yeah, the coarsening process is not included on this effective study. Yeah.
Yeah, I can understand. So graph coarsening, you can use any method in graph coarsening, right? You can try different type of graph coarsening method, and you can plug and play, right? You can just implement any kind of graph coarsening technique in this method, and you can still use, right?
Yes.
All right.
The more complex, the more better, the better.
Right. It's a very nice. It was a very nice talk, and overall the work also looked very nice to me. Thanks a lot, Dan. Thank you very much.
Yeah, thank you very much.
All right, so let's thank Dan once again for his nice presentation. All right, so we end this session. All right. Anything else, Aricho? I think everyone's waiting for the cultural program, so we're standing between that. So
no, we have a little time on stage left.
Oh, okay.
Please. So we've witnessed whatnot. We've witnessed monitoring systems, overlapping community detections, underwater image restoration, deepfake image detections, and personalized recommender systems. So, Partha, do you want to share anything, or we are concluding it, right?
No, I think it's absolutely fine. I saw really nice papers, a few papers, which were really nice, and lots of graphs, essentially.
So yeah, thank you, Partha. So with that, I would now request again Professor Prashanjit Gupta. He has been my guide when I started my PhD. Unfortunately, I haven't completed it yet. So to felicitate Dr. Partha Boshi Chaudhary. Please join me in giving both of them a great round of applause. Thanks. Okay, so with this, we conclude today's technical sessions. It's been a pretty intense couple of technical sessions with almost 8 talks and another invited talk. And after 2 days of such intellectually stimulating talks, which must have been very enriching and engaging for our audience, I'm sure our minds are craving something different. So we'll take a quick tea break, and at 6:30 we'll gather back here for a vibrant and captivating cultural evening, showcasing the artistic talents of our students and colleagues. They not only present technical papers and write research articles, they're adept at the finer arts also. See you back then.